Welcome back. So far, we've used several Unreal Engine classes from the class hierarchy, but we have not yet used the character class. Now, we've seen that the pawn class is derived from the actor class. Well, the character class is derived from the pawn class. So while the actor has its own capabilities, for instance, being able to be placed or spawned in a level, the pawn inherits those qualities from the actor class, as a pawn is an actor, but it also has its own characteristics that the actor does not have, such as the ability to be possessed. And the character inheriting from pawn also inherits the ability to be placed or spawned in a level, and also inherits the ability to be possessed, but it also has other more specialized characteristics specific to game characters. We'll talk about those now. The character class has a character movement component. As we saw with the pawn class, pawns do not automatically get a movement component. We had to add one. We added a floating pawn movement component to our bot pawn, for example. Well, the character class already has a movement component, and this character movement component is specific to characters. It moves characters in ways that characters should be moved. Characters also have a mesh component. So with our bot pawn, we had to add our static mesh component to it, but characters already have a mesh. Now, a character does not have a static mesh. It has a skeletal mesh component, which is different, and we'll discuss those differences soon. Characters also have an arrow component, which is something that you don't see in the game, but it's visible in the editor to show you which direction is forward for the character. Now, it's very common for the character class to have a camera component attached to a spring arm component, just like we did with our pawn. Now, this is not built into the character class, but I'll mention it here because it's one of those very commonly added things that just about all characters will have, at least those that will be controlled by a human player. Now, aside from these components, a character will also have a set of character-specific functions that the pawn class does not have. Now, we mentioned that characters have a skeletal mesh component, and that this is different than the static mesh component, which is what we've been using thus far. A skeletal mesh component differs from a static mesh component because it has a skeleton. A skeleton is a hierarchy of what we call bones. Each bone is skinned to the mesh, which means that when a bone moves, some of the polygons of the mesh move with the bone, and these are arranged in a hierarchy of attachment. So one bone will be attached to another bone in a sort of parent-child hierarchy. And these bones can get quite intricate, even down to the smallest appendages such as fingers. Now, skeletal mesh components do not have collision hulls. That's not to say that they don't have simple collision. Their simple collision comes in the form of a special type of asset called a physics asset. A physics asset can have multiple collision shapes, and these are attached to various bones, so when a bone moves, those collision shapes can move with it. We call these shapes physics bodies, and they can come in the form of simple shapes, such as capsules and boxes, etc. This allows for the mesh to move around in the world and animate, and those physics bodies will move along with that skeleton, allowing for a more dynamically moving set of collision shapes. So now that we've seen some of the differences in the character class, we're now ready to start creating our own, but we're going to need some assets for this next game project. So you're going to download the Jetpack sample project in the resources for this video, unzip it, and open it up. So I'm here in my Jetpack project, and as we can see, we just opened up to a default level called Jetpack level. which is pretty empty, but we have some assets in our content folder. And what I'd like to look at right now in the assets is the Kix folder, K-I-X. Kix is the name of this particular character, and we have some assets pertaining to Kix. The first one I'd like to take a look at is SKM Kix. Let's double click that. Now, SKM Kix is a skeletal mesh asset. As we can see, the naming convention is SKM Kix. SKM is short for skeletal mesh. And Kix is a nice stylized humanoid asset. Humanoid meaning it's roughly in the shape of a human. It has arms and legs and a head and a torso. And being a skeletal mesh asset, the asset has a skeleton. Now, we have a panel called the skeleton tree, which shows us the hierarchy of bones. These bones are each connected to one another in a hierarchical fashion. Every indentation indicates attachment. One bone is attached to its parent bone, and if its parent bone moves, all child bones move along with it. So each bone has its own individual transform. And these bones are skinned to the mesh. When one bone moves, it moves the polygons of the mesh itself according to how the mesh is weighted to those specific bones. Now, we can see the skeleton if we go up to Character, and under Bones, we can select All Hierarchy. If we choose that, we can now see all the bones, and we can click on them and select them. And we can see the names of those bones. And in the skeleton tree, we'll see them on the hierarchy as well. I just selected a Kix neck base joint bone, which is connected to another bone, which, as we can see, following the attachment chain, is attached to way up here the Kix spine joint, and multiple bones can be attached to a single bone. Now, we can rotate this bone here in the skeletal mesh editor, and notice that the mesh moves along with these bones. And we can see how moving one bone moves the child bones as well. And this is how animation is handled in a game engine. A skeletal mesh has a skeleton, which is weighted to the bones. Now, we can see the weighting of each bone if we go to Character, Mesh, and under Mesh, we can go all the way down to Selected Bone Weight. And if we select that, now I can see not only the polygons of the mesh, but the weighting of a given bone. I have this bone on the arm selected here, and where it's red is where those polygons are weighted to the bone the most. So it's color-coded in a sort of heat map. And that just means that if I move this bone, those red polygons move along with the bone, and the other polygons have less intense weighting to that bone. And we can even see that the fingers themselves have weighting, even down to the tiniest little appendage at the end of the hand there. So this can get quite intricate. So animation is handled by moving these bones, and the mesh moves along with the bones. And as we saw, the collision for a skeletal mesh component comes in the form of a physics asset. And we do have a physics asset called PhysKix. If we open that, we'll see those physics bodies. There doesn't have to be a shape for every single bone, but the ones that we do have are connected to the bones. And depending on the game, we may have more detailed physics assets or less detailed ones. So this is the simple collision for our skeletal mesh component. We'll go ahead and close that. Now, I did select the bones and moved them, but don't worry, as soon as I close this, those changes in the transforms of those bones will not be saved. So I'm going to go to Character under Mesh, and I'm going to select None under Mesh Overlay Drawing. Now we don't see those polygons and their weights. And I'm going to go to Character and choose Selected Only, And that way we don't see all the bones, we only see the bones that we've selected, and we can select them here in the skeleton tree. And as I said, if I close this and I open it back up, SKM Kicks, it's back in its base pose, so we haven't changed anything. Now, a skeletal mesh asset is associated with the skeleton, as we can see to the right, but we're in the skeletal mesh editor. There's also a skeleton asset editor, and if we double click on SkelKix, we'll see that this is the skeleton asset editor, and it looks a lot like the skeletal mesh asset editor, but we're just looking at the skeleton itself. And of course, we will see the mesh too, but this particular editor is just the skeleton editor. And at the top right, we have a set of icons, and we can switch between different asset editors because the engine knows that this skeleton is associated with SKM Kicks. So the first icon says SkelKix, and it has an icon of a skeleton. The next one says SKM Kicks, and it's an icon of a mesh. If I select that, now I've opened the skeletal mesh editor. The next icon over is for animations, and if I click on that, it's going to open the animation editor. And now we can see this animation asset that it just chose for me, and it's called AKix Idle, and it's showing me kicks in an idle animation. And in the asset browser to the right, we can double click on any of these animation assets, and we're playing those animations so we can see kicks, in this case, playing a grab animation. And we can also see the skeleton tree over here to the left and select bones and see those bones moving along with the animation. So animation assets, skeletal mesh assets, and skeleton assets are closely connected to each other, and that's why we can open those assets really quickly using the icons at the top right of these editors. So now that we know we have a skeletal mesh asset that we can use for a character, we can now begin creating the character class for this game project. And we'll do that in the next video. I'll see you soon. Welcome back. We're now ready to create our very first character class. I'm going to go ahead and close all the asset editors that are open and create a new folder in my content folder. So this one will be called Blueprints. We'll keep all of our blueprints in this folder. And in Blueprints, I'm going to make a new folder called Kix, K-I-X. Here in Kix, we'll create our character class. So I'm going to right-click, select New Blueprint Class, and for the first time, we're going to choose Character. I'm going to call this BP_Kix, nice and short, and I can open up BP Kix, and right away, I'm noticing that this asset editor has opened in a new window. I'd like it to open automatically docked up at the top, so I'm going to go to Edit, Editor Preferences, and change my asset editor open location to main window, so that won't happen again. All my asset editors will open docked at the top. Okay, so with BP Kix open, we can see what the blueprint looks like. We have a viewport tab, a construction script tab, and an event graph, much like actor blueprints. We even have those 3 grayed out events: begin play, actor begin overlap, and event tick. Now, let's go back to the viewport. Notice we already have a couple of things. We have what looks like a capsule and what looks like an arrow, and that's what those are. We have the capsule component and an arrow component as well. The capsule component for a character is the root component. Notice the pop-up says it cannot be renamed or deleted. Character classes have to have a capsule as their root component. This cannot be changed, so this is a limitation of the character class. Attached to the capsule, we have the arrow component and the skeletal mesh component. This component is called mesh, and it's inherited from the character class. And notice that beneath these components, there's a line under which we have character movement. This is the character movement component. It's separated by this line because character movement component does not have the ability to be attached to another component. It's based on the actor component class, but it does not have collision or the ability to be attached to other components. So components that don't need attachment do not exist in the attachment hierarchy that we see in the components panel. They exist by themselves beneath this horizontal line. Now, if we select the mesh component, we'll see in the details panel under mesh that it has a skeletal mesh asset variable. We've already seen that a static mesh component has a static mesh asset. So skeletal mesh components are similar, except their mesh asset is a skeletal mesh. So the character cannot have a static mesh assigned as the mesh asset for its mesh property. If we wanted a static mesh, we'd have to click Add and add a static mesh component and use that. But that's okay because we do have a skeletal mesh component that we can use. If we open the dropdown, this startup project already has SKM Kicks, as we've seen. So by selecting the skeletal mesh asset, we have Kicks, and notice that something looks off, right? Kicks is a little bit too high, and Kicks is also facing the wrong direction. And this is a very common situation you'll face in Unreal Engine when you create a character blueprint and assign a mesh to that skeletal mesh property. You see, the reason that it's facing the Y direction and not the X direction is because that's just how this mesh was created. Its pivot point faces the Y direction, and this is going to be very common. If you go to the Unreal Marketplace and you download a skeletal mesh asset, it will most likely be facing the Y direction. But that's okay because our mesh is not the root component. We can rotate it relative to the root component. So I can select rotation, and I can take the gizmo and rotate it by 90 degrees, and now Kicks is facing the character's forward direction, the X direction as indicated by the gizmo at the bottom left. Now we can also move Kicks down. I'll just hit W and move Kicks down slightly, but we're going to want Kicks to have their feet at the bottom of the capsule, and I'll show you why. Let's just go into our level here and drag our BP Kicks into the level and release, and just take a look at what happens here. The capsule is on the ground, the feet are above the ground, and that's because the character class uses this capsule component for lots of things. It uses the capsule component when placing the character on the ground. It's placed based on that root component. So the bottommost part of the capsule is what touches the ground. So we want our mesh to be on the ground based on the lowest point of that capsule. Characters also use the capsule component for lots of collisions. Yes, we have the physics asset if we want more accurate collision detection, but for most collisions, characters use this capsule component to detect collisions with walls, for example, with the floor, with the ceiling. It's the capsule that bumps into these objects and prevents the character from moving through them. So we also want that capsule's height to be appropriate for the Kicks mesh. So in the character blueprint, we're going to resize that capsule just a bit. By selecting the capsule component, we're going to change some dimensions on it. Now, we don't want to change the scale. What we want to change are the properties on the skeletal mesh component for the height and the radius. For the height, capsule components have a property called capsule half height. Now, we're going to click and drag it to the left until we have a bit shorter of a capsule. I'm just going to keep going until I see it just about at the right size. It doesn't have to be perfect. I'm going to enter in 75, and we can move Kicks down just a bit so that the feet are just about at the bottom of the capsule. So with a little bit of tweaking, we can zero in on some dimensions that look right. Looks like I set the capsule half height down to 70. And because my capsule half height is 70, I can also take my skeletal mesh component and go to its location here and see that -70 is its Z component. So that's going to put those feet just about at the bottom of the capsule. And we can go back to our level and move our character down to the floor, and we'll see that that looks just about right. Now, we don't want that radius to be too thin. If we wanted to, we could bring that capsule radius in so that it's about as thin as the head, for example. But if we did that, then we could bump into walls and we could see those arms passing through walls, which is not something we want. So I'm going to leave that capsule radius at about 34 to give us a bit of leeway, a little bit of space between walls and the character mesh. And now we have our very first character. Now, our project still needs a few things. If I press play, I'm not going to automatically possess Kix. I'm possessing the default pawn because we don't have anything telling our project to use this particular character blueprint as the default pawn. So we're going to need to do that. And we're also going to need to set up movement inputs so that we can move this character around. But for now, this is a good start. We have our character and we're ready to continue, and we'll do so in the next video. Great job, and I'll see you soon. Welcome back. Now, we need a few more things before our project is going to start feeling like an actual game. For one, we've seen that when we press play and start a Pi session, we just start possessing the default pawn. We want to possess our character class, this BP Kix character class. So to do that, we're going to create a game mode specific to our Jetpack game. And we can designate Kix to be our default pawn. So first, I'm going to go to my blueprints folder and make a new folder for game-related classes, such as the game mode. So I'll call this folder game, and in the game folder, I'll create a new blueprint class based on game mode base. I'll select that, and we'll call this BP Jetpack Game Mode. So this will be specific to the Jetpack game project. Let's open it up. And the first thing I'll do is go to the default pawn class, change this from default pawn to BP Kix, and compile and save. So now we have a game mode where Kix is the default pawn. We just need to make sure that the game mode is used by our project. If we go and press play, we're still just going to possess the default pawn because we're not using that game mode class. I'm going to set that game mode for our project. So I'm going to go to Edit and Project Settings, go to Maps and Modes, and change the default game mode from Game Mode Base to our game mode BP Jetpack Game Mode. Now I'm done with project settings, and if I press play, I'm now going to be possessing Kix. It's hard to tell, but if I go ahead and detach and move around, I can see that I was inside of Kix's head because we are now possessing Kix. And I can reattach, and I'm now on Kix, but of course we can't move. If I click to engage in the level, there's no WASD movement, there's no mouse movement, there's no way to move Kix at all because we have to set those things up as we learned in our previous project. We had to set up enhanced input, right? Now, another thing to keep in mind is if I press play and I go ahead and detach and turn and look around, I'll see that there's still that Kix character over there. We're actually possessing this new Kix that was dynamically spawned in thanks to the game mode. That one back there is just sitting there in the level. So that could be a source of confusion if your game mode is spawning in your default pawn class. You don't really need to have your character sitting in as an instance in the level, just there already. So I can take this instance of Kix, I can delete it, and now if I press play, I can detach and turn around and look and see that there's only one Kix, and that's the one that we are possessing by default. So now that we have a game mode for our game and we've set the default pawn class, we're now ready to continue developing our Kix character. I'll see you in the next video. Welcome back. In this video, we're going to add a camera and spring arm component, and you may have actually seen the title of this video and gone and done it yourself. Feel free to do that. You can go ahead and just pause the video and do it, or do it along with me if you like, but we're going to add a spring arm component and a camera component for our character. Now, these can be attached to our capsule component. So with the capsule component selected, I'm going to add a spring arm first, and we can just let it be called spring arm. And with spring arm selected, I'm going to search for camera and add a camera component. And now we have our camera. Now, I'm going to just leave it as is. I'm not going to rotate it by selecting the spring arm and changing its rotation. I don't need to do that. Once we configure input, we're going to make our camera move along with our mouse so we can look around and see Kix from different angles. Now, the spring arm target arm length is something we could adjust if we like. I might set it to 250 to bring it in closer, or I can bring it farther out. It depends on your preferences. But now if we press play, we can see Kix from behind, and we're no longer looking out from the inside of Kix's head, which is great. So now that we have a camera and spring arm, it's now time to set up input for our project so that we can actually move that camera and look around, and of course move our character as well. You may have noticed that our character has a jetpack on their back, and that is something that we plan on making fully functional so that Kix can not only run around, but fly around as well. So we've got some really exciting things in store for this game project coming up. Great job, and I'll see you in the next video. Welcome back. It's time to start implementing input for our character. And I'd like to start by being able to look around by moving my mouse. Now, we've seen in our previous game project that we could implement movement by creating enhanced input assets, such as input actions and an input mapping context. We're going to do that same thing in this video, except we're going to do things a little differently than we did for our bot pawn. In our bot pawn, we went to our event graph and we associated our input mapping context directly with the pawn, and we implemented functionality in the pawn event graph. Now, that's one way to do things. Another way is to implement movement on the player controller class. Implementing movement on the player controller allows us to keep our character class uncluttered so that we don't have too much functionality on the character class, and we're letting the controller handle the movement as a way to keep a separation of concerns so that we don't have too many things handled by any one given class. In programming, when one class gets larger and larger and handles more and more things, we call that a God class, and that's typically a pattern that we try to avoid. So first, we need input actions and an input mapping context. Now, if you feel so inclined and you'd like to get some practice trying this on your own, create an input action and an input mapping context for our Kix character. If you'd like, pause the video and do that now, and come back and watch the rest of the video, or you can just do it along with me by continuing with the video here. Okay, so what we're going to do is go into our blueprints folder, make a new folder for our input, associated classes. We'll go into Input, right-click, and make a new folder here called Input Actions. And we need a new input action. Now, this is going to be for looking around. That's a two-dimensional input. We have a mouse x-axis and a mouse y-axis. So let's make our new input action. We'll go down to Input and select Input Action. We'll call this IA Look. And IA Look can have its value type changed from digital bool to axis 2D vector 2D. And now we just need to associate this input action with our mouse XY movement. And we can do that with an input mapping context. So we'll go to Input, and we'll put our input mapping context right here. Right-click, Input, Input Mapping Context. We'll call this IMC Kicks Movement. The name isn't too important. And we'll open this up and add a new mapping here. Opening the dropdown, we can select our IA Look input action, and we just need to associate it with a given type of input. So I can open the dropdown, go to Mouse, and select Mouse XY 2D axis. So now we have an input mapping context, and we just need to associate it with our character. Now, I mentioned we're not going to put that association in our character blueprint, but rather in our player controller class. So that means we're going to need to create a new class for Kix's player controller. And that's where we're going to add our input mapping context and add the functionality to tie in our IA Look input action to moving our camera. So we'll create that new player controller class in the next video. Great job, and I'll see you soon. Welcome back. So we have Kix and things are looking great. We also have an IA Look input action that we've added to an input mapping context, associating this input action with the mouse XY 2D axis. And we mentioned that rather than adding the input mapping context to the BP Kix character itself here in the event graph, we're going to do this on the player controller class instead. And for that, we need our own player controller class. So let's go ahead and make one. We'll go to Blueprints. We'll make a new folder called Player. And here in Player, we can make our custom player controller class. We'll make a new blueprint class. We'll choose player controller. And I'm going to call this BP Kix player controller. Now we have a new player controller class, but that does not mean necessarily that we're going to be using it when we go and press play. In fact, we won't be if I press play and start a Pi session. What we have to do to use our new player controller class is we have to designate this player controller class as the default player controller class for this game project. And we know that we're using our BP Jetpack game mode. This is where we can specify the player controller class right here under classes. By default, it's set to the base player controller class, but we want our specific child of player controller called BP Kix player controller. So now that we've specified that class to be our player controller class, now we'll be using that. And we can prove that by opening our new BP Kix player controller. Here's the blueprint for it. We can go to the event graph, and look, our player controller class has a begin play. Why don't we prove that this is running by using a print string node? We'll print BP Kix player controller in the print string, and we can go and start a Pi session. And there we go. We see BP Kix player controller at the top left, which proves that our new player controller class is actually being used. And this is the player controller that's possessing our BP Kix character here. And in this player controller class is where I'd like to add our input mapping context and implement our look behavior. Now, before we go and do that, I'd just like to remind you how we did it before in our previous game project. We did it in the pawn class. We did it in bot pawn on begin play. And I'm going to run through that process just as a refresher so that you can remember what we did, and also so that we can see how that process is slightly different in the player controller class. So I'm going to delete these two nodes and leave begin play there, and remind you how we added an input mapping context to our pawn in begin play. We first called get controller and used this controller in a cast node. We used cast to player controller. And once we cast to player controller, we then had the ability to get what's called the enhanced input local player subsystem, this big fat node here. And from that local player subsystem, we were then able to call add mapping context. So we called this add mapping context function, specifying the mapping context. We could choose IMC kicks movement, for example. Once we did that, then we could go and search for the IA look enhanced action event, and we could implement movement functionality from here. That's how we did this on the pawn class in our previous bad bot game. Now we're going to delete these nodes because we're going to implement this on the player controller instead, but I want to point something out to you. Part of this process involved getting the controller that's possessing this particular pawn, casting it to the player controller class, just so that we could get the enhanced input local player subsystem from it. That's because this enhanced input local player subsystem is accessible from the player controller class. Well, our class BP Kicks player controller is derived from the player controller class. In other words, it is a player controller. So it just already has access to that enhanced input local player subsystem. So we can access it here in Kicks player controller just in the event graph. Let's do that. First, I'm going to delete my print string. I'm going to delete my event tick. I don't need that. And I'm going to search for enhanced input local player subsystem. I don't even have to type the whole thing. Now, there's a couple of options. One is get enhanced input local player subsystem, and this exists under something called local player subsystems. But there's also a get enhanced input local player subsystem under the player controller. Let's choose that one. Notice that this one has an input. If we hover over it, it says player controller object reference. So it requires an input because we need to get that enhanced input local player subsystem from a player controller. Now we can always right click and type self and get a reference to self, and we can plug that in to satisfy that input, and we can get the enhanced input local player subsystem that way. But let's right click again and search for enhanced input local player subsystem, and let's choose the other one, the one that's under local player subsystems, not under player controller. This one does not have an input. This just allows us to access the enhanced input local player subsystem from this player controller that we're in. So we don't have to pass in self, and for that reason, I like this one better for use within Kicks player controller. So we don't need to use the one with self, we can just use this one. Now back in BP Kicks, once we access that enhanced input local player subsystem, we were then able to call add mapping context. We can do that here in our player controller as well. We can drag off, type add mapping context, and get that function and call it on begin play. So as you can see, the process is actually a little bit easier on the player controller. We use less nodes because we don't have to access the controller and cast it to a player controller here. We're already inside of a player controller. So we already have access to that local player subsystem. Now we can just choose the mapping context, and we can simply select Kicks movement here, and now we've added that mapping context to this player controller. Now we can go back to BP Kicks. We don't need these nodes anymore. We were just looking at them for informational purposes. Now we can delete those, and we have our input mapping context added to Kicks player controller. And we can actually get those input actions. IA look is our only one. but we can get that here and we can test to see if it's working. We can print a string on triggered. And I can take the action value and just plug it straight in. And we'll get a conversion node from vector2d to string. And we can see if we press play and click and move our mouse, we can move left and right and see that we get a value for the x, the y stays at 0, but if we move up and down, then the y has a non-zero value, and we can move all around in the circles and change those values. So we can see that this is actually working, but we can actually remove that print string and go back to bpkicks and search for IA look here, and we also have access to the input action here. We can even print a string here, printing the value of action value. I'm going to change it to red or orange and play test and move my mouse. And notice that we also have access to that input action on the pawn itself. Here in the character blueprint, we can implement functionality here as well. So that's good to know. But we're going to implement our movement functionality here on the player controller class. And for looking behavior, this is actually kind of convenient because a player controller has its own rotation. And as we learned in our previous game project, we can just designate certain components on our pawn to follow the player controller. For instance, our spring arm component, this can be set to follow our player controller's rotation. Under camera settings, if we scroll slightly down, there's a checkbox that says use pawn control rotation. So if we rotate our controller, our spring arm will follow it if we check this checkbox. Before we check it, let's implement rotating our controller as a response to our IA look input action. How do we do that? Well, our player controller has functions for adding input to change its rotation. We have add pitch input. Let's get that function. And we have add yaw input. Let's get that function. We don't really care about the roll. We don't want to twist our player controller. We just want to rotate it up and down like it's nodding yes, and rotate it side to side like it's shaking its head no. If we call both of these on triggered, then we can pass in a value to rotate in the pitch and yaw directions. And remember, our action value can be broken. We can use a break vector2d to access the x and y. And the x is what I'd like to use for the yaw, and the y is what I'd like to use for the pitch. Now my wires are crossing, so what I'll actually do is swap them around like this. And now we're adding pitch and yaw input in response to IA look. Let's just go back and start our Pi session and engage and go ahead and rotate. Now I can rotate left and right, but I cannot rotate up and down. And another thing that I'm noticing is my actual character mesh is rotating along with my mouse as well. And I don't want that. I want my spring arm to rotate only and not my mesh. So let's go back and take a look at bpkicks. Now our character mesh itself is actually rotating along with the capsule component, which is following that controller. And this is because the character itself has a property called use controller rotation yaw. And that's set to true by default. If we uncheck that and go back and try to rotate, we'll see that nothing rotates at all. And that's what I want. I don't want my character itself to follow my controller rotation. What I do want is my spring arm to follow my controller rotation. So with my spring arm selected, now I have a use pawn control rotation checkbox. I'm going to check that and go back and play test. And now I can rotate both in the X and the Y directions. Now, when I move my mouse up, I look down. And when I move my mouse down, I look up. That's actually inverted from the way that I prefer, and you may not prefer it that way either. When I move my mouse up, I want to look up. In other words, I need to negate the Y value for my input action, IA look. So I'm going to go to my IA look input action itself, and I'm going to add a modifier choosing the negate modifier. And I only need to negate the Y axis, so I can uncheck the checkboxes for X and Z and go back and play test, and I can see that moving my mouse down looks down, moving it up looks up, and I can rotate as I wish. All right, this is looking and feeling a lot better, but I still can't move my character around. Pressing the WASD keys does nothing, so we still have some work to do, but we're getting there one step at a time. Excellent job, and I'll see you in the next video. Welcome back. Now our Kix character is starting to come along. We can rotate the camera around Kix, but we can't move our character. So we need an input action for moving the character around. And I'd like to use WASD movement, at least at first, to move the character. So we need an input action. Let's go ahead and create one. We'll go to Blueprints, Input, Input Actions, right-click and go to Input and select Input Action. And this will be IA Move. And much like IA Look, IA Move can be a 2D input action. So we'll make this Axis 2D, Vector 2D. And we need to add this to our input mapping context, of course. So we'll click plus to add a new mapping and select our new input action, IA Move. And we're going to want WASD movement here. So I can click on the keyboard and press W. That gives us the W key. We'll need to click plus to add more inputs. For the second one, I'll set this to A. We'll click plus, and for the third, we'll set this to S. And plus one more time and set the fourth one to D. Now, as we know, our input action has two axes, X and Y. And I would like left and right movement to be fed in to the X axis. And that's going to be A and D, A being left and D being right. And when moving left, I want that X axis value to be negated. So we're going to add a modifier to A and choose negate for that modifier and expand the dropdown and keep X selected and uncheck Y and Z. So even though all of our inputs feed into the X axis so far, A and D are the inputs we actually want fed into the X axis, and A will have its input value negated. W and S, however, should go into the Y axis, so we need to swizzle them. So for W, we're going to add a modifier and choose swizzle input axis values. We can expand it and make sure that Y is the first letter in the order. The others don't matter because we only want this input fed into one axis, the Y axis. And single keyboard keys and buttons only have one axis worth of data. So W now has its data passed into the Y. Now we need to do that with S as well. So we'll add a modifier to S, choosing swizzle input axis values. We see that Y is the first letter, which is perfect. But we also want to negate this value. So we're going to add a second modifier, and this one will be negate. And for the negate on this one, we want to negate the Y-axis so that when we press S, our input is scaled by -1. So we'll leave Y checked and uncheck X and Z. So S is the only input that has two modifiers. It needs to be swizzled because we're using the Y-axis, and it needs to be negated because we're moving backward. So now that we have WASD inputs set up in the input mapping context, we can now implement IA Move on our player controller. So let's go back to our player controller and implement IA Move. We can do so by right-clicking, searching for IA Move, and getting that Enhance Input Action event. And here we have the action value. And just to see that those values are what we expect, we can use a print string node, and we can take that action value 2D vector and pass it straight in to convert to a string. And let's just play test and see what happens when we press those keys. So I'm going to press W first, and we get 0 in the X and 1 in the Y as expected. I'm going to press A. We get -1 in the X and 0 in the Y. I'm going to press S. We get -1 in the Y and 0 in the X. And I'm going to press D, and we'll have +1 in the X and 0 for the Y. And that's exactly what I expected. So now that we've verified that our input action is set up correctly, we can now move the character. Now we have a character blueprint based on the character class, right? And the character class automatically has a character movement component. And the character movement component is designed to handle movement for the character. We don't have to set the character's location directly or add forces or anything like that. We add movement input to the character movement component. And the character movement component handles moving the character for us. And it has a number of parameters that allow us to customize that type of movement. It'll slowly ramp up the character's movement from a speed of 0 to a max speed. It takes care of applying gravity to our character, and it has a number of other parameters on it. All we need to do is pass an input vector to the character movement component to tell it that we're moving and to tell it what direction we're moving in. And since we're handling movement on the player controller, we need to access the character movement component on the character. Now, whenever we're in the player controller class, we can always access the pawn that our controller has possessed. We can do that by right-clicking and searching for the function getControlledPawn. This returns us a pawn object reference. Now, our pawn is actually a character, but we don't need to cast to the character class to access the movement component because the pawn class has a function getMovementComponent. If we call that, now we have a pawn movement component object reference. And the class pawn movement component is the parent class to character movement component. So the pawn class has a way to get its movement component if it has one, and our character is a pawn that has one. So this returns the movement component in the form of a pawn movement component. And the pawn movement component class has functions for adding movement input, and those functions are inherited by child classes that derive from pawn movement component. So we can add input to our movement component without casting it to a character movement component. So if we access the movement component, we can get functions like add input vector. This is how we add input to our movement component. It requires a world vector input parameter that'll tell us the direction and an optional Boolean. We don't need to worry about that for now. So let's see what happens when we add an input vector. I can remove my print string, and we can connect this add input vector function call. Now, we'll figure out what to do with this input action value in just a moment, but for now, I'm just going to add an input vector in the world X direction. I'm going to hard code the vector 1, 0, 0. This is a unit vector pointing in the X direction, right? Let's see what happens if we go and press play, and we press any of the WASD keys. I'm going to press W, and I'm moving forward. But this is a problem. If I press S, I also move forward. If I press D or A, all of these move me forward. So we're just hard coding that X world direction in to add movement input. But as you can see, we smoothly start moving forward according to that input vector that we pass in to add input vector. So this is a way that we can move our character We just need to figure out what direction we actually want to move in. And the direction that I want to move in is a direction determined by my controller. Because as I move my mouse, I'm moving my controller. I'm rotating it. And I want to get that control rotation, the rotation of my controller, and move forward in that direction. So if I'm looking at my character from this angle and I press W, I want my character to turn and start walking back that way. And if I'm looking at it from this side, I want my character to turn to the right and start walking that way. I always want to move in the direction that my camera is looking in. So I need to get the controller's rotation to do that. So back to Kik's player controller, I'm going to figure out that direction from my controller's rotation. Now, the controller itself has a function to get its own rotation, and it's called getControlRotation. If we call that, we get a rotator. And we want a vector corresponding to this rotation. And we know that we can get a vector from a rotator with the function getForwardVector. GetForwardVector requires a rotation and returns a vector pointing in the forward direction of that control rotation. That's the direction we're looking in when we're moving our mouse around and rotating that controller. So getForwardVector gives me that direction that I want. And this is perfect when I want to move forward. In other words, when I'm pressing the W key. So I'm going to get my action value, but rather than getting it here and using breakVector2D and getting the X value from that, instead I'm going to get my action value as a standalone node by searching for IAMove and getting the enhanced action values IAMove Blueprint Pure node. So I don't need to break this one and drag my wires across. I'm going to break this one. Now, rather than dragging off and using breakVector2D, I can simply split my struct pin by right-clicking on it and choosing Split Struct Pin, and that gives me one less node. And I can get my Y value. Remember, W and S are being fed into the Y-axis of my action value. And Y is going to be 0 if we're not pressing the key. It'll be 1 if we're pressing W, and it'll be -1 if we're pressing S. So if I simply take this forward vector and multiply this by the Y value, then it'll be pointing in the opposite direction when pressing S. So if I'm looking forward and I press S, this vector will be pointing backward. So I can right-click, convert this to a float, and pass in Y for it. And this can be the vector we pass into addInputVector. I'm going to go ahead and pass that right in. And now we can go and play, and I can engage and press W and move forward. I can press S and move backward. And the cool thing is I can rotate my controller to some other angle and press W, and we're moving that way. So I can move around with W and S, and I'm going in the direction I'm looking in. And that's the type of movement that I want for this character. But we can only move forward and backward. We can't move left and right. So we need to handle that as well. And what we can do is the same thing that we're doing here, except we can get the right vector of our control rotation. So we're going to get the control rotation. I'm going to duplicate that node. And instead of the forward vector, I'm going to get right vector this time and multiply this. But I'm not going to multiply by Y. I'm going to multiply by X on our input action. So I'm going to duplicate these nodes and simply change the float that I'm multiplying by to the X value on IAMove. And we're going to call addInputVector a second time, passing in this vector. So calling addInputVector twice is going to tell the movement component, I want to move in this direction, but I also want to move in this direction, and the movement component is capable of combining those two input vectors, but still managing the speed of the character according to the parameters on the movement component that determine how fast the character should move. Now, add input vector does require a pawn movement component object reference. So I do need to get controlled pawn and get movement component from it. So I'm going to duplicate those nodes over here and pass those into the target. And now we should be able to move left and right. And playtesting, we'll use A to move left, D to move right, and now we have WASD movement. And we can move our mouse to look around and control which direction we're going in with both mouse and keyboard. Now, yes, I know the character is just standing idle. It's completely frozen, and we need to change the animation poses based on movement. We'll do that soon enough. For now, it's enough to just program movement, and we have that. Now, I'd like to use the console command, show collision. So pressing the tilde key and typing in show collision and hitting enter, now we can see those collision volumes associated with our mesh. We have the capsule, we can see that, and we have a bunch of smaller capsules. Those are those physics bodies on the physics asset. Now notice as I'm orienting my controller and rotating it around, not only is my character's mesh staying still, but so is that capsule, which is the root component. But there are parameters that allow us to follow the control rotation if we want to. We've seen one of those. If we go back to BP Kicks, select BP Kicks self in the components panel, so we're looking at the actor as a whole, we can search for control, and under pawn, we have variables for inheriting the controller's pitch, yaw, and roll. And then we have the character movement component variable, use controller desired rotation. So before we wrap up, we're just going to briefly look at what these do. First, let's look at the pawn variables, use controller rotation, pitch, yaw, and roll. First, I'm going to check use controller rotation yaw, compile, and press play, and engage, and we'll see immediately that our character's mesh rotates. But if we enter show collision, we'll see that the capsule rotates as well. So it's actually the capsule that's rotating along with the controller, because our pawn's use controller rotation yaw is selected, and this just designates our root component to follow the control rotation. And we have rotation pitch and roll as well. Now we're not really changing the roll, but we are changing the pitch of our controller. So if we check that checkbox, let's see what happens when we change our controller's pitch. Take a look at that. It kind of looks like we're flying, right? It's not a good look. It doesn't look right. So use controller rotation pitch in our case is not something that we would want. In fact, I really don't want to use controller rotation yaw either. So I'm going to go ahead and uncheck both of those. Now, the character movement component has a separate Boolean variable called use controller desired rotation. And the pop-up says, if true, smoothly rotate the character toward the controller's desired rotation using rotation rate as the rate of rotation change. Well, we don't see rotation rate here because we filtered the details panel with control. But if I search for rotation instead, we can see that rotation rate down here along with use controller desired rotation. So I can check use controller desired rotation, and I see the rotation rate, and it has 0, 0, and 360 in that final value there. Let's see what happens if we go ahead and start moving. If I rotate my controller very quickly, we'll see that our character is rotating to use that controller rotation, but it's not doing so very quickly. It's taking a second to rotate in that direction, and that's according to that rotation rate. We're basically smoothly interpolating towards that control rotation using the rotation rate. That's what use controller desired rotation does. There's another option orient rotation to movement. If we disable use controller desired rotation and instead check the checkbox for orient rotation to movement, now we're going to orient according to how we're moving. So for instance, if I move to the right, my mesh turns to the right. If I move to the left, my mesh turns to the left. So we're always going to rotate in the direction that we're moving. And that rotation happens according to that rotation rate, which we can change. If 360 is too slow, we can change it. Let's change it to 720 and go back and move around. And we'll see that that rotation rate is higher and we're rotating faster. So these are properties on the character movement component, as we can see by the category here, character movement. And we can prove that by selecting the character movement component, and we'll still see those properties, rotation rate and orient rotation to movement. So now we know what those two Booleans do. And it's important to understand what these do because we may have conflicting settings. We may have orient rotation to movement set to true, but if we go back onto the pawn and check use controller rotation yaw, well, now we have two conflicting settings. One setting on the character movement component says we should orient rotation to movement, and another setting says we should use our controller's rotation yaw. Now, if we go back and press play, we're going to use the controller's rotation yaw because that's something that sets the pawn's rotation every frame. And if we try to move, now we're fighting ourselves. We're trying to orient rotation to movement, but we're also trying to orient rotation to the controller's yaw as well. And so we get this jitter because the two settings are conflicting. And that's not what we want. We never want incompatible settings. So it's important to understand the settings so that we don't have two settings set that are fighting against each other. So if we want to use the controller's rotation yaw, we can't orient rotation to movement. I want to orient rotation to movement, so I'm going to uncheck use controller rotation yaw. And now I have movement that is closer to what I want. I can run in a particular direction, and my character is going to orient in that direction. I just need my character to actually play a running animation when my character is actually running. And we'll get to that soon. For now, we're doing a great job. Now, the feet are not quite planted on the floor, and I can fix that by going to BP Kicks, selecting my character mesh, and moving it down ever so slightly. I may want to disable snapping for this, and just move it down a little bit and play test and see what that looks like. It's not quite low enough, so we'll move it down a little more. And now it looks like it's actually on the floor. So sometimes this can be an iterative process to get it just right. I see that -73 is about right, and that plants my character right there on the ground. Excellent. Great job, and I'll see you in the next video. Welcome back. Before we move on, it's important to keep our blueprints clean and tidy, and this is something we should do at every stage of development. So I'd like to clean up our player controller nodes so that everything looks nice and clean, and the more complex our project gets, the easier it will be to maintain this way. So we'll start with begin play. We'll add our mapping context in a function designated to handle that. So I'm going to right-click, collapse to function, and we'll call this add mapping context. And we can keep these in categories. Add mapping context is related to input. So with add mapping context selected under functions, I can go to my details panel and enter a new category. I'm going to call this kicks input and compile that. And the next function we make will also be related to input. I'd like these nodes to be encapsulated in their own function. And this is for adding the yaw and pitch input for IA look. I'm going to collapse this to a function and call this add look input. And this can take that in action value. It's a vector 2D. Instead of invec, we're going to call it action value. And add look input can also go into that category kicks input. So it'll be right there in that category. And already our blueprint is looking better. Next, we have IA move. Now, we're doing a couple things here in IA move. First, we're getting the forward vector from our control rotation and scaling it by our action value's Y axis. So really, this is getting our forward input action. So I'd like to collapse these to a pure node. So let's collapse to function, and I'm going to call this get forward input. And I'd like this to be a pure function, so I'm going to check pure, and now we have get forward input. Now, the names here should be descriptive of what we're doing. Get forward input is pretty good. It doesn't quite tell us that we're getting the forward vector of our control rotation, but as long as we understand that, that's fine. And we can set this to have the same category kicks input as well. Now, we're getting the controlled pawn and getting the movement component, and you might be wondering, is this more expensive than, let's say, caching off this value, storing it in a variable on the player controller? And it's slightly more performant to do that because calling get controlled pawn is a function call. There's an indirection associated with that in the flow of execution. And once the pawn is accessed, another function is called to get the movement component. That's another indirection in the flow of execution. So technically speaking, it's slightly more performant if we were to store this movement component as a variable. And we can do that in begin play if we'd like. Here's what we would do. We would copy these nodes, come up here into begin play, paste them here, and take that movement component and promote it to a variable. We can call this movement component, and we can store that. And instead of calling these two function nodes whenever we need the movement component, we can now access it via the member variable movement component. And I can collapse this to a function. I'm going to call this store essential variables. And this doesn't have to come after add mapping context. We can have it before or after. So I'm going to put it right there before add mapping context. And now we have a movement component variable, and we don't have to make these two function calls. We can simply get the movement component variable and pass that in instead. And it's a good idea to make sure that that variable is valid before we use it. So I'm going to duplicate it, and for this duplicate, I'm going to convert to a validated get. And we'll only perform these actions if is valid is the case. If it's not valid, we won't continue. So now we have add input vector for the forward input. I'd like to do the same for the right input. So I'm going to collapse these nodes to a function and call this get right input. And this can be converted to pure and also given the category kicks input. And like we did over here, we don't need to call two functions. We can simply access one variable, our movement component variable. So now these nodes look a lot better. And all of this is doing one thing. We're adding movement input. So we can collapse these all to a function, and we'll call this add movement input. And we could pass that action value in as an input, but as you could see, we didn't need to because our pure functions just access those via the get IA move node. And if we really wanted to, we could come back to add look input and eliminate that action value as an input altogether if we just wanted to get the IA look input action value right here. So there's always more than one way to do things. It doesn't really matter in this case. We don't have to eliminate the action value and get IA look here and replace this. But if you wanted to, you could. And just to show you that process, I would just replace X and Y here, eliminate the break node, and then select Add Look Input and eliminate the input by pressing the X. Now it's gone, but if we go to our event graph, our Add Look Input has a wire going in where there's no longer an input. And to fix that, we right-click on it and we refresh the nodes, refresh nodes, and now we don't have an input. So I didn't have to make that change. You could just pass it in as an input. Either way is completely fine. There's no significant performance difference between the two ways. So now our player controller is looking much better, and it makes sense when we look at it. Input action IA_Look calls a function called add_look_input. We don't have to worry about what it does, and if we do need to know what it does, we can just double-click to go inside of it, and we see that we're calling two functions using the input action values. And these are functions on the player controller class. And if you really wanted to see what these functions did, well, then you'd be going into C++ code because these are C++ functions. So now our player controller is looking better. We can see the nodes required for movement. Things are looking great. We're ready to continue, and I'll see you in the next video. Welcome back. Now, we have movement, which is great, and I know you're dying to get some animations on Kix, and we will very soon, but before we do that, we're going to implement jumping. Jumping is essential, and it's a relatively simple thing to implement. So we're going to do that really quickly in this video. For jumping, we just need a simple input action. So we're going to go to our input actions folder, right-click, go to input, select input action, and this will be called IA_Jump. An IA_Jump can be a digital bool. We just need to know on or off. Are we jumping or are we not jumping? So now that we have the input action, we can go to the IMC Kix movement input mapping context and add a new mapping and scroll all the way down to the bottom and select IA_Jump and find it, open it up. And this is going to be tied to the spacebar. So I'm going to click on the keyboard, press the spacebar, and now we have the spacebar. And we're going to implement this. And we could implement it right here in the player controller by right-clicking, choosing IA_Jump. And I'd like to jump when we press the spacebar, not every frame while it's being held down. So I'm going to use started. Now our pawn is a character, and the character class actually has a function for jumping. If we go back to BP Kix and search for jump, we'll see that there's a function called jump. And it says target is character, meaning that this is a function on the character class. And this handles jumping for us. Now we have two options here. We can simply implement IA_Jump on the character class right here. And we can hook up started to a function call to jump. This is a very simple and straightforward way to do it. BP Kix implements its own jump. We can go ahead and test this even by pressing play, pressing the spacebar, and we can jump. And that's great. But we wanted to handle all movement on the player controller. So rather than doing this in BP Kix, I'd like to keep that movement code out of Kix and in the player controller. And to do that, I need to get my controlled pawn with get controlled pawn. But jump is on the character class, not the pawn class. We've seen this issue before where we needed to access something on a child class, but we only have that data in the form of the parent class. This is what casting is for. So if I cast to character, now I can access that function, jump, because the cast gives us our controlled pawn cast to the character data type. Now, casting is the type of operation that can affect performance in various ways, and we'll talk about those a little bit later in this section. In general, if we cast, we want to try to keep casting to a minimum, and if we hook this up to started, we'll be casting every time we trigger this input action, which will work, and that's fine, but if we can avoid casting multiple times in a row unnecessarily, that would be ideal. But just as is, we can go back and play test, and we'll see that pressing the space key does work. We can jump, but we're casting every time unnecessarily. So in order to avoid multiple casts to the same data type, we can simply cache the variable. We can perform the cast once and begin play, and then we can access the character every time we need it. So I can go back up to begin play, and we have a function for storing our essential variables. We can do the cast in here. We can get our controlled pawn, and we can cast it. So I'm going to get controlled pawn, cast to character, and once we've cast to the character class, I'm going to take that character and I'm going to promote it to a variable, not local, and this variable can simply be called controlled character. It's the controlled pawn cast to the character class. We'll go ahead and hook this up, and now we have a controlled character variable stored on begin play. Yes, we're performing a cast once, but we're not performing it every time we try to jump. Now, as I mentioned, we'll talk more in future videos about what casting is doing from a performance standpoint, especially when it comes to memory. But for now, we've made this optimization where we don't have to cast multiple times. So back to our event graph, we can go back down, and instead of casting our controlled pawn every time, we can simply get our controlled character and call jump on our controlled character. And it's a good idea to make sure our controlled character is valid. So I'm going to convert this to a validated get and hook that up to started so that we only call jump if our controlled character is valid. And I can collapse IA jump, and now we have our jump functionality. And I'm going to take my controlled character variable and just give it its own category. I'm going to call it essential variables. And I can even take my movement component and change its category to essential variables, and now they're both there together. And it's always a good idea to play test. Let's just make sure jumping still works. It does, and we don't have to cast every time. Okay, so now we have looking input, movement input, and jumping input. We're almost ready to dive into animations, but before we do that, I'd just like to do one more thing, and that's implementing our input using a console controller, like an Xbox controller or a PlayStation controller. I'd like to briefly show just how easy it is to do that, and we'll do that next. I'll see you soon. Welcome back. Now, we have movement with mouse and keyboard, but it's actually pretty easy to add movement for console controllers. Now, for this video, you're going to need a console controller that you can hook up to your computer in order to playtest this. I have an Xbox controller that I can hook up via a USB cable. And if you have an Xbox controller or a PlayStation controller, or just some generic controller that has a USB cable, you can plug that into your computer. So I'm going to go ahead and plug in the USB cable for this controller now. And you'll see that as soon as I do that, we get an input device has been connected message. We can check the checkbox to not show it again. I'm just going to leave it there. But now we know that Unreal Engine has detected an input device. So now that we have an input device connected, we can playtest controller input. Now, the first thing I'm going to do is go to my input mapping context and add controller input to my input actions. We'll start with IA look. Now, IA look uses mouse XY 2D axis as the input. And IA look is indeed a 2D input action. We can verify that by opening IA look and seeing that its value type is axis 2D. Well, I'm going to add another input to IA look by clicking the plus right next to the IA look dropdown. And now I have another input. And for this one, I want to use my controller's right thumbstick. So I can take my drop down and expand gamepad. And we have the thumbsticks for gamepads here. I want the right thumbstick. And notice that we have X and Y axes as well as a 2D axis option for both the left and the right thumbsticks. I'm going to choose gamepad right thumbstick 2D axis. And now this input is connected to IA look, which is already implemented. Now we can play test this. As soon as I press play and click to engage, well, I notice a drift. But as long as I'm actually moving my thumbstick, it looks fine. I can move left and right, up and down, and I'm moving my camera. But as soon as I stop, we have a drift. And that's because there's a tiny amount of input that is being fed in, and we don't want that tiny amount of input. This is due to the inaccuracy of floating point values. So if I go back to IMC Kicks Movement, I can add a modifier that will prevent any input if that input value is close to 0, according to a certain threshold. For input, we call this a dead zone. There's a zone on our controller where if we're not pressing enough, it's considered to be an input of 0. Let's add that dead zone. Now we can add it here on the IMC, or we can add it for the input action itself. I'm going to add it right here. So I'm going to add a new modifier, and from the dropdown, I'm going to select dead zone. Now there are parameters for the dead zone, such as the threshold for lower and upper, as well as the type. We want to leave that at radial because we're using a 2D axis. Radial is for the thumbstick's 2D axis as a whole, whereas axial would be for one dimension if we were only using the X or just the Y, for instance. Now I'm going to leave the dead zone's parameters at their defaults and just go back and play test again. And as we can see, we have no drift. I can take my controller, move to the left, move to the right, up and down, and everything is working. Now, when I move my controller up, I'm looking down. And when I move it down, I'm looking up. That's not what I want. I want that Y-axis inverted. So just like we did with our IA look input action, we applied a modifier to IA look itself. We're going to want to negate our thumbstick input. So essentially, the IA look is already negated. That results in the behavior we get with our thumbstick and our mouse. But for the thumbstick, it's not what we want. So we need to go back to our input mapping context and negate it here for our thumbstick specifically. So I can add another modifier and choose from the dropdown negate, and we can negate the Y. We don't want to negate the X or Z. And now if we go back and play test, when I move my thumbstick up, I look up. When I move it down, I look down. So our right thumbstick controls our camera, which is great, but we can't move around with our left thumbstick, which is the behavior that I want. So let's add the left thumbstick to our movement as well. So we're going to go back to IMC Kicks Movement. I'm done with IA look. I'm going to collapse that. And now for IA move, I want to add the gamepad left thumbstick. So I'm going to click plus. That automatically expands IA look again, which is a little annoying, but I'm going to collapse it back and collapse WASD. And we have our next input. I'm going to choose gamepad. And this time we're going to use the left thumbstick 2D axis. So with just that change, let's go back and press play. And let's move our left thumbstick. And as we can see, it's moving our character. But again, if I release, we still have that drift. So just like with our right thumbstick, we need a dead zone. So on the gamepad left thumbstick 2D axis, we're going to add a modifier and choose dead zone. And I'm going to leave the dead zone parameters as is and play test. And once again, we can move our left thumbstick, but when we stop moving, our character stops moving because we have a dead zone. So dead zones are very important when it comes to controller input. Now, something I'd like you to notice, thumbsticks are pressure sensitive, unlike WASD keys. So both of our thumbsticks, left and right, are pressure sensitive. If I barely push my thumbstick just past that threshold for the dead zone, we get a small value for the input, less than 1. And we can rotate our camera very slowly if we want to. Or we can rotate fast by pressing the thumbstick all the way. And the same goes for movement. We can barely press that thumbstick and we can move in our input vector direction a very small amount, or we can press the thumbstick all the way and get full-on movement. Pressing it all the way is the movement we get when we press the WASD keys. But we cannot get that input value that's smaller, less than 1, with a keyboard key. A thumbstick, being pressure sensitive, allows us to get those smooth values, and that can be very desirable in a game where you might want to move slowly for any reason. And we'll see how to take advantage of this pressure sensitivity when we implement movement animations, allowing us to blend between walking and running. And we'll get to that soon. So we now have movement input for looking and for moving, but not yet for jumping. So the last thing we need to do is add gamepad input for our IA jump input action. So I'm going to click plus next to IA jump, and from the dropdown, we'll go to gamepad, and what we want is our gamepad face buttons. On a gamepad, these are the face buttons. For Xbox, they're X, Y, A, and B. Of course, they're different for PlayStation, and they may be different depending on the generic controller that you have, but I would like to use the bottom gamepad face button. So that's going to be gamepad face button bottom. And if I were to click on this button and simply press one of these buttons, we can assign that button that way as well. So the shortcut works when doing that as well. So now that I have gamepad face button bottom tied to my jump, I should be able to jump with my controller. So pressing my A button, in the case of my controller, I see that I get jumping. So now I have movement, looking around, and jumping, and I can use all three of them together to get a nice, natural feeling character locomotion system. And it feels and looks great. It's a lot easier for me personally to control a character with a console controller. And even if you're developing a game that's designed for PC, you may want to implement controller input anyway, and just have that as an option for players who want to play your game if you'd like to add that extra level of control. And then later, let's say you get a deal and your game is released to one of the consoles, well, you've already implemented console controller input, and that's one important step that you've already taken care of, and you don't have to do it just for releasing to a new platform. So that's console controller input, and as you can see, because we've already done the hard work with keyboard and mouse input, adding those controller inputs to our input mapping context was relatively simple. We didn't have to go into our player controller and change how we use that input, which is nice. Excellent job, and I'll see you in the next video. Welcome back. Now we have movement, which is great, but Kix is just standing in this T pose. It's actually more like an A pose because the arms are not quite straight out, but regardless, Kix is not moving. Now, we do have animation assets in this project. That's partially why we started out with this game project, and in the assets folder, if we go to Kix, we can open the animations folder and see all the assets that we have. Now, rather than standing in an A pose, I'd rather have Kix stand in an idle pose. Notice that my animation assets are all prefixed with A, and their asset type is animation sequence. If I double-click A Kix idle, I can see what A Kix idle looks like, and it's basically Kix standing there and breathing, and this animation is just looping over and over again. And if we go to asset details, we'll see that this property called loop is set to true, which designates this animation to simply loop when it's played. Now we can see what this looks like on our Kix character. If we go to BP Kix into viewport, we can see that there's Kix with the A pose, but if I select the mesh and search for the animation section here, animation mode is a property with a dropdown, and by default it's set to use animation blueprint. We can change it to use animation asset, and now we have an anim to play property. This is an animation sequence, and we can choose an animation to play. I'm going to choose A Kix idle. And we have looping and playing variables. We can uncheck looping, and we'll only see it play once. Even though our animation asset has looping on it, this particular anim to play property depends on looping being checked if we want it to loop. We can also uncheck playing, so we won't even see it there. And if we check playing, we'll see that animation playing. And this does play in the game. If we play the game, we'll see that there's Kix, and Kix looks a lot cooler with an animation playing like this, so this is great. Now, the problem with this is that Kix is just in the idle pose, and it doesn't matter if we're moving, Kix is just in that idle pose. If we jump, if we look around, it doesn't change that idle pose because it's playing a single animation asset. What we want to do is change that pose. We want to change the animation that we're playing. And this often involves blending between animations. If I start running or walking, I want Kix to smoothly blend into a running or walking animation. And for that, we have a new type of asset that we're going to create called an animation blueprint. So let's get that created. I'm going to first close all my tabs at the top. I'm done with everything that we had open there. I'm going to save all my progress, and we're going to create an animation blueprint. Now, I'd like to go to my blueprints folder and find Kix and put my animation blueprint here next to my BP Kix character blueprint. In some projects, you'll see the animation blueprint in the assets folder right there with the other animations. You could put it there as well. I personally like to keep my animation blueprint next to the character blueprint, at least for a simple project where I have one animation blueprint used by one character. So we're going to create it here. And to do so, we right-click, go to Animation, and select Animation Blueprint. As soon as I choose that, I'm prompted with two choices: use a specific skeleton or create a template animation blueprint that is not specific to a skeleton. That's a little bit more advanced. We're going to choose specific skeleton, and we only have one skeleton asset in our project to choose from. That's SkelKix. We're going to choose that and click on Create. And we typically prefix our animation blueprints with ABP, short for Animation Blueprint. I'm going to call this ABP Kix. And we'll go ahead and double-click it to open it up. And here is the Kix Animation Blueprint. Now, notice to the top left, we have a viewport. I can hold Alt and left-click and drag to rotate around the character, and right-click and drag to zoom in and out. I can resize the windows if I want to see it bigger. And this viewport shows us an example of what Kix will look like based on the poses that we've configured. An animation blueprint also has an event graph and an anim graph. The event graph is a lot like event graphs in actor blueprints, where we can script out logic, and this is typically where we update variables that we're going to use to drive our animations, to select poses. And those poses are selected in the anim graph, where we have an output pose node. Now, it has an input called result. And if we hover over it, it says animation pose. And here we can choose animations to play for our character. And to the bottom right, we have an asset browser with animations. This is open by default. If you accidentally close it with the X, you can go back up to Window and find Asset Browser and get it back. And by default, we see a bunch of animation assets that use the skeleton that we chose for this animation blueprint. If we had animation assets that use a different skeleton, we would not see them here. It's filtered out. And we can bring in an asset. I'm going to choose A-Kicks Grab and drag it in and release. And we get a node that says Sequence Player. This will play an animation sequence, specifically the animation sequence that I dragged in. And in the Details panel at the top right, we can see that that sequence is a property here. We can change what that sequence is from the dropdown by selecting a different animation sequence here. So this node has an animation sequence, and notice its output pin has a little human icon. It says animation pose, and we can connect that to our output pose. Now look at our viewport. Kicks is still in the A pose, right? But if we compile our animation blueprint, now Kicks is in that grab pose. We played the grab animation, and we only played it once. Now, we could loop this animation by selecting the Sequence Player node, going to the Details panel, and checking Loop Animation. And if we compile that, we'll see in the viewport that we're looping the animation. So this animation blueprint so far is quite simple. It just plays a single animation on looping, but we can apply this animation blueprint to our Kicks character by opening its character blueprint, BP Kicks, selecting our mesh, and going to our animation section and changing animation mode from Use Animation Asset to Use Animation Blueprint. And here we can select the anim class from the dropdown. Now, it shows a lot of classes built into the engine. We just want ours, ABP Kicks. Now, if I go to my viewport, notice that Kicks is playing that grab animation on repeat. And that's because it's actually using the animation blueprint now. So if we go and press play, we're playing that grab animation. Now, this is not ideal, right? We want to run when we're moving, not play a grab animation, but this is just an example of how our animation blueprint is driving the pose of the skeletal mesh component that has assigned it in its anim class property. And animation blueprints are great for changing the pose based on data. And in order to have data to use to decide which pose to play, we update that data in the event graph. We have an event here called Blueprint Update Animation. It even has a delta time, and this is much like tick in actor blueprints. It's called every frame. So we can see if this is working by adding a print string node to it. And notice there's a grayed out node try get pawn owner. This is a function on the animation blueprint that returns the pawn that owns this animation blueprint. That's the pawn that has it assigned to its skeletal mesh component by selecting anim class. So if we take this try get pawn owner and drag it straight into print string, we'll get a get display name node, and we should be seeing that every frame. And if we go and press play, we'll see that that is BP Kicks 0. So ABP Kicks has access to the pawn that's using it. And this is what we can use to determine what animations to play by getting that pawn owner and getting properties from it, such as seeing if it's moving or not. We can see if it's moving by getting its movement components. We can use get movement component. And from movement component, we can just see how fast we're going. a movement component has a velocity variable. And if we get that velocity, we can see if that velocity is 0. The vector type has a vector is 0 function that returns true. I'm going to plug that straight into my print string so that I can see if my velocity is 0. If I go back and press play, I'll see true printed to the screen. But if I move, now it says false. If I stop, it says true. And if I move, it says false. So we know every frame if our character is moving based on its velocity. This is a very rudimentary way to know. So for a simple example of how we can change our pose, I'm going to store this Boolean in a variable on the animation blueprint. We can have variables on our animation blueprint. So I don't need my display name anymore. I'm going to highlight all these nodes and press Q to straighten them out. And I'm going to promote this Boolean to a variable called isVelocity0. I'm going to hook that up, and every frame we're updating our Boolean isVelocity0. Now I can use this in my anim graph. I can blend between two animation poses based on a Boolean. I can do that by right-clicking and using a special node designed for the anim graph called Blend Poses by Bool. If I get that Blend Poses by Bool, notice it has some inputs. It has a true pose, a false pose, and an active value, as well as blend times that specify how quickly we should blend into the true or false pose. The smaller the value, the quicker we blend. This is an amount of time to blend. So I can use isVelocity0. I can drag that straight in from my variables onto the active value. And if this isVelocity0 Boolean is true, then Blend Poses by Bool is going to output whatever pose we have here for our true pose. So I can bring in my kicks idle pose, and I can play that as my true pose. I'm going to go ahead and delete my kicks grab sequence player, and instead plug in my Blend Poses by Bool to the output pose. And I need a false pose too. So when isVelocity0 is false, that means I'm moving. So I'm going to play my run animation. I have an A kicks run forward animation right here. And by the way, if you want to see what these animations look like, you can hover over the animation here in the asset browser to see it moving, or you can double click on it to open that animation asset, or you can double click on the node itself, the sequence player node, to open that animation asset. Notice we got those print strings here in the viewport in the animation asset editor as well. That's because we haven't compiled our changes yet. As soon as we compile, now our updated changes are applied. And notice that our animation blueprint is running even when we're not playing the game, as indicated by these wire animations. We're showing our output pose evaluated based on these values. So let's go back into the world, press play, and we see we're in the idle animation. And if I run, I'm in the running animation. Now it's not looping, so that's a problem, but we've seen how to loop that animation pose by going back to our animation blueprint and selecting the sequence player node and checking the checkbox or loop animation. So I have it checked for run forward now. And if I go back and press play, now I'm looping that running animation. And if I stop running, now I'm in the idle animation. So Blend Poses by Bool is an example of how we can use a variable, some piece of data, to drive our animation pose. We're choosing between one or the other based on a Boolean value. And before wrapping up, just to show how the animation is blending, we're going to up the blend time to 0.5 for true blend time and 0.5 for false blend time. And we're going to start running. And notice that it takes a second to blend into that pose. Specifically, it takes half a second because our blend time is 0.5, and it takes half a second to blend out of that pose. And it's painfully apparent when these values are too high. I'm going to set them to 2 each and start running, and it takes a full 2 seconds to blend in and a full 2 seconds to blend back out. And we can see the effects of blending animations at play here. So it's a good idea to tweak those values until they look good. I'm going to leave them at 0.1. We're actually going to get rid of this blend poses by bool node and see a better way to blend our animations in this manner very soon. But now we can see that it's quite easy to drive our animation poses from data using our animation blueprint by harvesting data in the event graph, storing that data in a variable, and then using that variable to drive animations in the anim graph. We'll continue with this in the next video. Great job. I'll see you soon. Welcome back. Now, what we've implemented so far looks good. We're in the idle animation when we're not moving, and if we start moving, we're in the running animation. Now, this looks pretty good, except when I grab my console controller and apply that pressure-sensitive input. If I barely touch that left thumbstick, I'm moving very slowly, but I'm still playing that running animation at full speed, but I'd rather play something else, like a walking animation. In fact, we can see what a walking animation looks like by going back to our ABP Kicks animation blueprint, opening our anim graph, and changing our Kicks run forward animation by opening that details panel, finding the sequence, and finding a Kicks walk forward. Now we're going to play a walking animation instead. So if we press play, and I barely touch that thumbstick, now I'm walking and it looks normal, depending on the speed. But as soon as I push that thumbstick all the way, well, now I'm at a running speed and I'm still playing the walking animation, and that doesn't look right either. So what we need is a way to blend between our animations based on our speed. And ideally, we should blend between that walking animation and the running animation, and even that idle animation, depending on how fast we're going. Now, to blend between animations, we can use an asset called a blend space. We can do so by right-clicking in our content drawer. I'm right here in my Kicks folder under Blueprints, and going to Animation, and there's an asset called Blend Space. But if we go to Legacy, there's also a Blend Space 1D. For what we're doing, we could just use a Blend Space 1D, but I'm going to show you the regular Blend Space first. So let's choose Blend Space. When we choose Blend Space, we have to pick a skeleton, and as soon as we do, we can rename our asset. I'm going to call it BS for Blend Space, and we're going to call this Idle Walk Run. And as soon as I open it up, we see our blend space asset. Now, a blend space allows us to put a bunch of animations on a grid and blend between those animations based on values. We can place a series of animations left to right, and we have a horizontal axis as shown on the bottom going from 0 to 100. And this blend space will turn into a node that we can add to our anim graph in the animation blueprint and pass data into it. So if I search my asset browser, I now have BS Idle Walk Run here, along with my other animation assets. If I bring in BS Idle Walk Run, notice I have 2 float inputs. Both are called none. And this blend space outputs an animation pose that we can hook up to our output pose. Now, what are these inputs, both called none? Well, if we go back to our blend space, these are the axes on our grid. We have a horizontal axis, that's the first none, and a vertical axis, that's the second none. Now, none is a horrible name for axes. So what we can do is go up to our axis settings in Asset Details and expand these dropdowns. Our horizontal axis, called none, needs to be renamed. And I'd like to blend between idle, walk, and run animations based on a speed variable. So I'm going to rename my horizontal axis to speed. Now, as soon as I do that, I can go back to ABP Kicks and see that my BS idle walk run blend space has speed for its first input. And the second input is still called none, and we don't really need that one. That's why I said we could use a blend space 1D. A blend space 1D is the same thing, except instead of a grid, we have one dimension, a single line going from left to right, and we don't have a horizontal axis. But we can still use this blend space and simply not use that second axis. And if we go back to our blend space node in the anim graph and select it, in the details panel, we can take that none axis and hide that input pin. We don't need to use it. We can open this dropdown and uncheck expose as pin. And now our blend space only has a single node for speed. Now back to our blend space, we need to decide what values our horizontal axis should take. And then we need to bring in some animations that we can play when our speed variable passed in is a certain value. Now, if we go to BP Kicks and select the character movement component, under walking, we'll see that we have a max walk speed. It's set to 600 centimeters per second. By the time we reach 600, I want my character Kicks to be in the running animation. In fact, I want it to be in the running animation well before that. So what I'm going to do in my blend space is set the maximum value for my speed horizontal axis to 600. And now we can see that reflected at the bottom right. So we're going to drag in some animations here, and we're going to drag them all onto the bottom line where this vertical none axis is 0, because we're never going to pass in a value for none into our blend space node. So when my speed is 0, I want to be in the idle animation. So I'm going to drag in a Kicks idle right here, and I want it to snap to that bottom corner, so I'm going to hold the Shift key to snap it. If you hold the Shift key down, we can snap to increments on the grid. I'm going to leave that there. Now, when I'm walking, I want to be in the walk animation, and I want to see what my walk speed will be when I'm at the perfect speed for my walk animation. So what I'm going to do is go to my ABP Kicks event graph and find that speed. Now, I'm only interested in the X, Y components of my velocity to calculate my speed. I don't care about the Z component, how fast I'm moving up and down. I just want the lateral speed. So I can take my velocity and type vector length, and we have vector length XY, which will only take into account the X and Y components of this vector. And I'd like to print the value of this vector length XY. So I'm going to use a print string node and hook that in and just see what that value is as I'm walking. And I'm going to use my pressure sensitive console controller as I'm walking so that I can see exactly how fast I need to be for this walk animation to look good. If I go too fast, I'm sliding. If I go too slow, my feet are also sliding, so I need to find that happy medium. So it looks like about 168 is the right speed for my walking animation. So I'm going to try that value on my blend space, about 168. So I'm going to get my walk forward animation, and as I'm dragging it around, I can see my X and Y values. I want to go to about 168, perhaps 170 here, but I want it down here at 0. So I'm going to drag all the way down and get my speed value at about 170 or so. And now I can see my Kicks character blend between these on my grid by holding down the Control key. And I can drag left and right and see what my animations look like for various values of speed. And at about 168, 170, I'm in the walking animation. And beyond 170, I want to blend into my run forward animation. as long as I'm playing that animation before I reach 600, I'm good. So I'm going to drag it in and snap it to right about the middle, 300 and 0 for the none axis. And if I hold Control, I can show what that looks like blending from walking into the running animation. So now we have this asset called a blend space, and we can use values that we pass into that node in the anim graph for speed to drive that pose. And that's what we're going to do. We're going to cache off our speed in a variable. But I'd like to clean this up a little bit. So we're going to do things a little differently here. For one, I don't want to call two functions just to get a value from our movement component. We're going to cache off some values, and we're going to do that at the beginning rather than every frame. And there's a function kind of like begin play for animation blueprints. It's called blueprint initialize animation. Here is where we can get our pawn owner, our character movement component, and so on, and we can cache those off. Now, what I'd like to do is get my pawn owner and cast it to a character. That way we have access to everything on the character class. So I'm going to cast to character and promote this to a variable, and we'll call this character. And as soon as we've done that, I can now get the movement component, and if I'm getting it straight from the character class, I can actually get character movement. And if I scroll down, there's a variable called character movement, which is of type character movement component. We can promote that to a variable, and I'm going to call this character movement. So now we have not only the character that owns this animation blueprint, we also have its character movement component. And I'm going to collapse this to a function called store essential variables. So now we have those variables stored, and we can access properties from them here in update animation. Now, I'm not going to use isVelocity0 anymore, so I'm going to go back to my event graph and simply delete where we're using it there. We're going to use the blend space now instead. And that means in the event graph, I don't need isVelocity0. I'm going to delete those nodes and delete isVelocity0. Instead, we're going to get our ground speed. So I'm going to get my character movement component, get velocity from that. That's a variable of type vector. And we're going to get the vector length xy, and we're going to promote this to a variable, and I'm going to call this ground speed. Now, as soon as we have ground speed hooked up to event blueprint update animation, we'll have this variable updated every frame as long as our character movement component is valid. And we can make sure of that by converting this to a validated get so that we only get this value if that character movement component is valid. So if this gets called before store essential variables successfully gets that character movement component, well, we won't try to access something that isn't valid yet. So now that we have our ground speed, we can go back to our anim graph and pass ground speed into our blend space and hook that up to our output pose. So now that we have a blend space being used instead of a sequence player, we're going to blend between our idle, walk, and run animations depending on what value is passed in to the speed input to this node. Let's see how that looks by pressing play. And I'm going to grab my console controller, and I'm first going to just run. I'm going to go full speed, and then I'm going to barely touch my left thumbstick. And as I'm barely pushing it, I can see that I'm in the walk animation, and as I push it harder, I'm going into the run animation, and we're blending. Now, if you don't like how it looks, you can always tweak your blend space, move those animations around, and get it looking just right, but this is looking pretty good. The only thing is I'm in the run animation while I'm going a little bit too slow, so I can move that run animation forward just a little bit and play test. And really, this is an iterative process. You might find yourself experimenting with it until you get it right. the most important thing is that that animation matches your speed at full speed. So as I'm running at full speed, 600 units, it's important that we don't get much sliding. And if there is sliding, you can do one of two things. You can speed up the animation, or you can slow down your character's movement speed by changing max walk speed. I'd like to speed up my run animation to accommodate for my running speed. So I'm going to take my kicks run forward animation. I'm going to double click on it, and I'm going to change its play rate here. Notice its rate scale is 1.5. So it's actually going faster than this original asset looked like. We can put it at 1 to see the original run animation speed. That's a little slow, so I'm going to set it to 1.65, and we're going to play test and run at full speed and just see how that looks. And I think that's looking better. All right, so we now have a blend space, and we're able to blend between walking and running animations, and things are looking great. And now that I'm walking, I'm seeing the feet go a little bit into the floor. So I would like to go to BP Kicks and raise that mesh just a little bit. We don't need to be quite so low. So I'm going to raise it a little. And we're going to check out how it looks. It's okay if we're a little bit above the ground, as long as we're not going too far into the ground. And I think that's looking great. So now that we have a blend space and we're walking and running and blending between the two, it's now time to implement jumping, and we're going to do that next. I'll see you soon. Welcome back. Now that we have a blend space to blend between walking and running animations, it's time to implement jumping. Now back in our animation blueprint, we see that in our event graph, we're updating our ground speed variable. And this can drive our blend space to blend between idle, walking, and running animations. But for jumping, we're going to need to do something a little bit different. Let's take a look at the animations we have for jumping. We actually have 3 main jump animations, not counting jump double, that's different. For regular jumping, we have jump start, jump mid, and jump end. I'm going to double click on jump start, and this is what it looks like. It's a beginning jumping animation. We also have a jump mid, which is more a falling animation. It's the middle of the jump animation, and it's a loop. And then we have a jump end, which is a landing animation. Now, the reason these 3 animations are separate and not one big jumping animation is because in our games, we may be in the air at varying times. If we're just on a flat surface and we jump and land, we can be sure that jumping will take the same amount of time, roughly every time we jump. But if we're up on a high ledge and we jump down, then we'll be in the air for longer, and we need to be playing that falling loop animation, jump mid, while we're falling. And we can't play that jump end animation until we actually hit the ground. So this is why we typically break jumping into 3 animations like this. So we need to know whether or not we're in the air. And that's going to require another variable. We can use a Boolean for whether or not our character is in the air. We can get that from our character movement component. If we take our character movement component and drag off of it, there's a function called isFalling. And this function, if we call it, returns a Boolean value. And we can get that value and store that in a variable here on the animation blueprint so that we can use it in our anim graph. Now, just to make sure things are tidy, we're going to move this variable updating business into a function. So I'm going to collapse it to a function and call this update animation variables. And that way, our event graph is going to look nice and clean, and we can do our business here in update animation variables. And here, the first thing I want to do is make sure the character movement component is valid, but I'm going to break this pin and move these nodes up and just use the character movement component from a get node here. And that way this can be separate and we can access the character movement component again after. So it's just a way to keep things tidy. I'm also going to add a reroute node here so that we can move this entire section around as a whole. And I'm going to comment this and say store ground speed. And just to make this nice and pretty, I'm going to give it a bluish color. I'm going to store that color here at the top. Click OK and check show bubble when zoomed. Now, I'm going to do several things, and I'd like to use a sequence node to keep them organized. So I'm going to use a sequence node here. The first thing we do will be to store the ground speed, and then next we're going to call is falling. So I'm going to use a duplicate of the character movement, get node, and call is falling. I'm going to highlight them, press Q to straighten them out, and I'm going to promote this return value to a variable, not a local variable, but a variable on the animation blueprint, and this will be called is falling, or we could call it is in air. That way it's a little more descriptive for what we're using it for. So we'll connect this to the sequence node. I'm going to double click the wire to give it a reroute node, highlight the reroute and is in air and press Q so they're exactly aligned. And I'm going to comment this part and say store is in air. We'll give it a color. I'm going to choose that same blue and check show bubble. So we now have two things we're doing in update animation variables. And we now have a Boolean for when we're in the air. This is all necessary so that when we go back to our anim graph, we now have a Boolean we can use in our anim graph. So how are we going to use it? Well, this is where a new concept comes into play, the concept of state machines. You see here in the anim graph, we can only plug in a single pose to our output pose, unless we're blending poses with some other node. You may have thought, well, maybe we can blend poses by bool, like this, and hook in is in air, and for false, we can plug in the BS idle walk run, but what do we pass in for true? The thing is, we need to blend between animations based on where we are in that jump cycle. As soon as we press the spacebar or the A button, we want to jump, but we want to play the beginning jump animation, that jump start, this one here, and then as soon as that animation has played, we want to move right into jump mid and play this falling animation, and then as soon as we hit the ground, we want to play jump end. And so things are going to get a little bit complicated if we blend poses using bools. What we can do instead is make a state machine. Here's how we do it. We right-click here in the anim graph, we search for state machine, and choose state machine. Now, this state machine is going to be called locomotion, and it's going to handle the locomotion for our character. Notice it has an output animation pose. We can plug it straight into our output pose here. But what is this pose? Well, that depends on what's going on inside of our state machine. If we double click it, we'll open it up, and we're here inside the locomotion state machine. And it's tabbed here at the top, and we can always go back to the anim graph by clicking here on anim graph. And now notice we have an anim graph and a locomotion tab, and we can go back and forth between the two. So locomotion is a state machine, and in state machines, we have states. A state can be added by right-clicking and selecting Add State. And we need a name for the state. This state is going to be called Idle Walk Run. And whatever we put in Idle Walk Run is what our locomotion state machine will return as the output pose if we're in this state. And by default, we can go straight to this state by dragging our entry node over to Idle Walk Run and connecting it with an arrow. So what pose is in Idle Walk Run? Well, we can double click it and go into it and determine what pose we get here. We can drag in individual animations and get sequence players and use that. Or we can use a blend space. And in our case, we're going to use a blend space. I'm going to drag it straight onto the result node so it connects right away. And I don't need that none axis. So like we did with my other blend space node, I'm going to find none and uncheck expose as pin. And we need to hook in a speed variable. That's going to be ground speed. And so this is our idle walk run state in our locomotion state machine. And if I click up here on locomotion and go back to my state machine, I see that it's just a state machine with one state. We go to it by default, and in our anim graph, this locomotion is going to output the pose dictated by where we are in our state machine, which is our idle walk run state. So back in our anim graph, we don't need this blend space node. We can delete it. And now our anim graph looks like this. We're driving our animation based on a state machine. If I compile, I'll see those wires animated. And if I press play, well, I now have my state machine dictating my pose, which is simply my idle walk run state, which contains my blend space. But now that we have a state machine, we can go into locomotion and we can have more than one state. We don't have to just have idle walk run. We can have multiple states, and we can have them connected with arrows. If I drag off of the edge of my state, I can add a new state. And I'm going to call this state jump start. And jump start can have my jump start animation inside of it. If I double click, I can come in here and bring in my jump start animation, make sure it's connected, and now my jump start state has an animation pose. So when do we transition from idle walk run to jump start? Well, that's where the transition rule comes in. You see, this arrow is a transition from idle walk run to jump start. And in order to make that transition, we have to set a rule for when that should happen. And we can do that by double clicking on the transition rule icon here. And this has a result node, which is a Boolean, can enter transition. I want this to succeed when is in air is true. So if I bring in is in air and hook that up, now my transition rule is dictated by the is in air Boolean variable. So if we go back to our locomotion state machine and hover over the transition rule, we'll see it says is in air. So we start off in idle walk run, but as soon as is in air becomes true, we transition to jump start, and we stay there. We never come back to idle walk run because there's no transition going back the other way. Let's just see how this works by pressing play, engaging in the game, and jumping. So we played the animation once, but we stayed in that state machine because we never transitioned back out of it. And we're not even looping the animation. So we're at the end of that jump start animation, and we're stuck there. Now, once we're finished with this animation, I want to transition into a new state, a state with the jump mid animation. That's this one here, the one where Kix is falling. So we need a new state in our state machine for the middle of our jump. Now, I could right-click and add a state. I'm going to delete that. I could drag off of a state and add a state. I'm going to delete that too, because there's a third way to add a state that automatically has an animation in it. That's just by clicking on our animation, dragging it in, and it's highlighted so we can rename it. I'm just going to call it jump mid. And if I double-click it, you'll see that that animation is already here. Except this is a looping animation, so let's select it and make sure that loop animation is checked. So now it'll loop. And we want to transition from jump start to jump mid as soon as jump start is done. In other words, we want an automatic transition from jump start to jump mid once jump start has finished playing. And we can achieve that by selecting our transition rule. We don't have to double click it to open it. we just select it, and there's a checkbox in the details panel called automatic rule based on sequence player in state. So the sequence player inside of the state for jumpstart is the Kicks jumpstart animation. This transition rule can transition automatically based on that sequence player that's inside of the state if we check the checkbox. And now as soon as jumpstart's sequence player, which is this node here, the jumpstart animation, as soon as that's done playing, we'll automatically transition to jump mid. Let's see what that looks like. By pressing play and jumping, we'll see that we're now stuck in that jump mid state, which is playing the looping jump mid animation. Now, you may have noticed that our jump start is a little slow. We might want to play this a little faster. So we can select that animation and we can scroll down in the details panel to the settings. We can increase that play rate. Let's try 1.65 and let's go back, play test and jump. Now that looks better, but we jumped a little earlier than our animation. In fact, I kind of don't want to play the beginning of that animation. I just want to play from about here, which is about 0.2 into the animation, 32%. But we see from a time perspective, it's about 0.2, 0.22 into the animation. That's in seconds. So with my sequence player selected, I'm going to start my sequence at 0.22 right here by setting my start position to 0.22. So we're playing it a little faster and we're playing a little bit into the animation. Let's go ahead and jump. And I think that looks a little bit better. Now we're stuck in that falling animation, so we need to get out of it. And we want to stay in that falling animation until we're no longer in the air. So we can drag a transition rule all the way back to idle, walk, run. And this transition rule can be based on is in air. So let's open that transition rule by double clicking it and drag in is in air. I'm going to hold Control to get a get node, but we don't want to plug in is in air because we don't want to transition when is in air is true. We want to transition when is in air is false. So we can get the opposite value of is in air with a node called not Boolean. If we get a not Boolean node, we're going to negate this value. If it's true, not will return false. And if it's false, not will return true. We're getting the opposite of is in air, which is what we want here. So I'm going to connect that, highlight my nodes and hit Q to straighten them out, and go back to locomotion. So now when is in air is false, we'll go back from jump mid to idle, walk, run. So we have this loop here. So let's see how that looks by play testing and jumping. So as soon as we hit the ground, we'll go back to our idle, walk, run. But we also have a landing animation, don't we? So we can use that as well. So holding Control and clicking on that arrow, I'm going to get rid of it. And I'm just going to get my jump end animation here and rename it to jump end. If I double click it, I see the jump end animation. And I want to transition from jump mid to jump end when is in air is false. So I'm going to go into this transition rule and get is in air, get a not Boolean, and hook it up. And we're done. And back in locomotion, from jump mid to jump end, we transition if is in air is false. And from jump end, I want to go straight to idle, walk, run automatically. So I'm going to drag a transition rule, select it, and check automatic rule based on sequence player and state. So when jump end is finished, then we'll go back to idle, walk, run. So let's see how this looks. Now we're playing that landing animation. Now I'd like to play a little bit into the landing animation. I don't want to play it from the exact start. I'd like to play it from about here, which is about 0.12. So I'm going to take that jump end, scroll down in the details panel and set the start position to 0.12. and I'd like to play it a little faster, about 1.5, but we can tweak that and we'll test it out, and that looks better. And I'll grab my controller and test with my console controller and just make sure that that feels good, and it does. So we now have a jumping animation. Now you might feel like Kix's movement is a little bit floaty, that once we jump, we're not going that high, but we're still staying in the air a little bit longer than you might think. And these are parameters that we can adjust for our character. So in the next video, we're going to do some tweaking of our parameters to get that character movement feeling exactly how we want it to feel. But for now, we have jumping, we have running, things are looking great, we have our basic locomotion for our character. This is a great milestone, so congratulations, and I'll see you in the next video. Welcome back. Now we have walking, running, idle, and jumping, right? And I mentioned in the last video, you might not be happy with your jumping. You might want a more stylized look. In other words, we might want to jump higher but fall quicker. And there are other various movement parameters we might want to tweak as well. So we're going to talk about some of those in this video. The first thing I'd like to do is jump higher and fall quicker. So I'm going to go to BP Kix and select my character movement component. And here is where we can change some aspects of our game. For instance, gravity scale. By default, we fall in a specific way, but we can scale that. If I set this to 2 or 3, I'm going to set it to 3, then when I jump, I'll be falling to the ground faster. It's like having a stronger gravity force. Now, I'm almost to the ground as soon as I've jumped, which is not good, so I need to jump higher as well. So back in BP Kix, I want to scroll down to my jumping/falling and change my jump Z velocity. For my stylized games, I like to increase this to a nice high value. I'm going to try 1200, and we'll see what this feels like in the game. So I'm going higher, and I'm falling to the ground faster. And if you want this to be even more stylized, more platformy, kind of like Mario, then we can make this jump Z velocity higher. I'm going to try 1600. Notice that it changes to 16 meters per second as soon as it's a larger value. It was centimeters before, so don't go changing it to 1600 meters per second. That's way too high. And we'll change our gravity scale to about 5, and we'll see how this feels. So we're falling faster and we're jumping faster. So this is a way to get a little bit bouncier movement, not so floaty, and ultimately these values are going to depend on your game. I'm going to up it to 1800, and I think that's feeling pretty good. So that's jumping, but what about movement? Notice that as soon as we start pressing WASD keys, we're actually not going full speed right away. There's a ramp up. There's also a ramp down, a slowdown that we can't really see that well, but we can if we adjust the walking parameters. If we scroll up in our character movement component, we'll see that we have a max acceleration, a braking friction factor, and under walking, we have ground friction. Now, if you don't want to slow to a stop at all, you can set ground friction to a higher value, such as 10. Then, as soon as we stop moving, we stop immediately. We can also do away with that ramp up by increasing our max acceleration. If I set this to a very high value, such as 100,000, then as soon as we start going, we go immediately. See how jerky it is? Now, with the console controller, we still have pressure sensitivity, but if I quickly press all the way, then we start moving right away. So there is no ramp up, and generally you want some ramp up. So I'm going to go ahead and set that back to its default value by hitting the curved arrow. But it's there in case you'd like that type of movement. Now, if you want to be able to control the character in the air, for instance, as soon as you jump and you're going one way, if you'd like to turn around and go back the other way while you're in the air, well, that's called air control. And if you go to your character movement component under jumping, falling, you can take your air control and increase that value. 0.6, for instance, will give us a lot more air control. If we jump and we turn around, we'll be able to influence where we're going, and a value of 1 is full air control. But this is full air control only at max speed of max walk speed, which means if we want to always go max speed without a ramp up, we'll set max acceleration to a high value. We'll go 100,000. And with a value of 1 for air control, notice I can turn around mid-air and go the other direction instantly. So this is not realistic, but for a stylized, more platform kind of game, this might be what you want. You might want to be able to run up to the edge of a cliff here and completely jump off, but turn around and come back. There might be a pickup that you can grab up there in the air, and then you can come back to safety. So that may be what you want, it may not be. With no air control, I would go flying off that cliff no matter what my inputs are after I've jumped. So because this is a stylized platforming type game, I'm going to keep a large max acceleration and air control of 1, just because I find that to be a little bit more fun and kind of fitting for the style of game. But choose the values that make sense to you. Now, the last properties I'm going to touch on in the character movement component involve stepping and walking on the ground. These are under the walking category. The first one I want to look at is max step height. Now, if I create a mesh, let's just say I go to modeling mode, choose box, and for the height, I choose 45. And I bring in a mesh. I can create this mesh. I'm going to go to Assets, make a new folder called Meshes, and I'll just put it here. We're going to create this. I'll click on Accept, Shift 1 to get out of modeling mode, and I now have a box. Let's see what happens when I try to step on this box. Remember, its height is 45, right? So I'm going to press play. And notice I can step up onto the box, no problem. We can see what the capsule is doing by showing collision. Here's my collision capsule, and it just goes right up onto the box, right? That's because my max step height on my character movement component is 45. If I bring it down below 45, now it's almost 42. If I run up to my box, I can't step on it anymore. Its height is 45, my max step height is less than that. Now, if I bring it up above the ground and I change my max step height to 100, well, we can try to step on it now, and sure enough we can, because the max step height is 100. So that's a property that allows you to dictate how easy it is to step up onto objects based on how high they are from the ground. 45 is the default value. I'm going to reset that. Now, related to step height, we have walkable floor angle, and that's set to 44.76, just below 45 degrees. So this determines how steep an angle can be before we can no longer walk on it. I'm going to scale this rectangle up and rotate it by 45 degrees. I'm going to set snapping increments to 15 and rotate it to 45. So we have a nice steep angle. Let's see if we can run up that wall, and no, we cannot. If I take this slope and bring it down, I'm going to set this to snapping by 5-degree increments. Now we have less than 45, and I can run up that slope. So that property on the character movement component, walkable floor angle, determines how steep an angle can be before we can run up that angle. If I increase it all the way to 90, then we can basically run up walls because our walkable floor angle is 90. If I bring this up to almost 90 degrees, let's make it something like this. Well, I can run all the way up that wall, which doesn't necessarily look that great. So you don't really want that high of a floor angle. I'm going to leave it at its default, which is just below 45. As soon as an angle is 45 degrees, it's barely too steep to walk up, and that's generally pretty good. So that's walkable floor angle and max step height. If you're having trouble running upstairs in an asset pack or a ramp or getting over obstacles and you're like, well, this isn't that high, why can't I walk on it? Go into your character movement component and adjust those values too. So those are some properties on the character movement component. Adjust those until you get things feeling and looking exactly how you want them to look in your game, and your games will feel a lot more responsive and less like the default mannequin that you get in an Unreal Engine template project. So many games just leave those default settings, but that's not appropriate for all game genres. If your game project requires a different feel, then you might want to go in and tweak those settings until they feel good. Excellent job, and I'll see you soon. Welcome back. We're going to cover a handy feature of animation blueprints in this video. Here I'm in my Locomotion state machine. I went ahead and closed one of the tabs because I had two Locomotion tabs up there. Now here's what my state machine looks like. And if I go and find my Kix player controller, here's what my logic looks like for implementing the jump input action. We're calling jump, and this logic is hooked up to started, which means that we'll only jump as soon as that jump button is pressed, and we'll only jump once. But if I hold that jump button down, we won't keep jumping. We'll hit the ground, and we'll only jump again if I release the button and press it again. But the jump function can be called continuously, and if it's continuously called, we'll continuously jump if we're not in the air. So really, if we wanted, we can go to Kix player controller, and instead of calling this on started, we can call it on triggered. If we do that, and we press play and hold that jump button down, we'll keep jumping, except notice that we play the full jump land animation and then the full jump start animation, so it doesn't quite look right. It would look better if we could go straight to that jump start animation as soon as we touch the ground and skip out of that jump end animation. We don't want to play the whole thing if we're still in the air, if we're still jumping. So what we can do is go back to our Locomotion state machine, and we can take our jump end animation and add another transition rule going back to jump start if our is in air boolean is true. So we can open this transition rule, use is in air for it, and now if we're in the jump end animation and we suddenly are in the air again, we'll go back to the jump start animation. So if we hold that space key down, well, now we're going straight back to that jump animation, and we can get this sort of bounciness, this bouncing behavior. So we can continue jumping. Now, the feature that we're going to cover is a feature designed to make our state machines a lot neater. See, we have a state here, jump start, with two transitions going to it. And both of them use that same is in air boolean as their transition rule. And state machines can get way out of hand, just like event graphs can in blueprints. And it's a good idea to use all tools that we have to keep them neat and tidy. Well, the tool that I'm going to use is called a state alias. If I right-click, I can choose Add State Alias, and I can give this a name. I'm going to call it toJumpStart. Now, toJumpStart can replace these two transitions because they're both going to jumpstart. if I select my to jumpstart state alias, I can select which of my states should have a transition going to where my jumpstart points to. For instance, I can have it going to jumpstart, hence the name to jumpstart. And I can take my transition rule and give it that is in air boolean and come back out. And I can remove these transition rules from jump in to jumpstart and from idle walk run to jumpstart. And instead, I can select my to jumpstart and I can select those states that I want to have transitions to jumpstart. One of them is idle walk run, so I check that checkbox. And the other is jump end, so I check that checkbox. So now these two nodes have transitions to jumpstart, but we can't see them. They're now here because of my state alias to jumpstart. So with this, I don't have to have so many transitions. And I can have a transition to jumpstart from literally any state. I just have to check the checkbox next to that state's name. And provided that my transition rule is appropriate for those states, this will work. If it's not, I can drag a second transition rule and I can have two of them. And I can double click the second one and put whatever condition I want here as well. But I don't want to, so I'm going to remove that one and just keep the single state. And by the way, states can have rules going both ways if you want. So these can get quite complicated. So it's a good idea to keep them nice and organized. So now we have the ability to hold down the jump button and continue jumping. And as soon as we're playing that jump end animation, if we're continuously pressing that button, we'll start that jump start animation. So that's a nice trick that you should use in your animation blueprint state machines. Excellent job, and I'll see you soon. Welcome back. Now, I'm sure you've noticed that Kix is wearing something on their back. It's actually a jetpack. It has two jet thingamajigs. I don't know what they're called, but they are supposed to blow fire out of the holes. So for that, we need some fire. Luckily, this game project has fire. If we go to our assets folder to effects and we check out thrusters, here is a Niagara system. Let's double click that. And here's what it looks like. I can right click and zoom in, middle mouse click and bring myself up. And I can look at this beautiful stylized jet thruster effect. What I'd like to do is see Kix blasting fire out of that jetpack, both holes. So in order to put one of these Niagara systems on the mesh, it has to go on the mesh in a specific location. And on top of that, it needs to follow along with the mesh. In other words, I want to attach it to one of the bones on the skeleton. Well, two to be exact, because we have two jetpack thrusters. And for that, sockets are a perfect solution. Now, we can add a socket and we can attach a Niagara system to that socket. So that is my goal for this video. So how do we add a socket to a skeletal mesh? Well, we can do so by finding that mesh. I can select the mesh on Kix and browse to it and open up the skeletal mesh editor, and I can actually add sockets to the skeleton from here. I can also add sockets to the skeleton from the skeletal mesh editor by either opening up the skeletal mesh here in the content browser or by clicking on the skeleton icon and going to the skeleton asset editor. I personally like to do things in the skeletal mesh editor, but that's personal preference. So we can add sockets to bones and we can attach things to those sockets. So I'd like to add two sockets to Kix's skeletal mesh. Now, which bones do we want these sockets on? Well, here's the spine bone. That might be good, but these jetpacks kind of move according to animations. So it might be a good idea to preview Kix in an animation while we're deciding which bone to put our socket on, because this spine 1 is right here. That's not exactly the best spot to shoot flames out of. It would be kind of funny. But we can preview an animation on this mesh by going to Preview Animation and selecting one. Now we have some flying animations. I'm going to select Kix Fly Idle. As soon as I select that, now we can see Kix in a flying animation. And look at those jetpack thrusters. They're animating. So we might not want to put those flames on Kix Spine 1. We might want to find a different bone. So I'm going to scroll down and, oh, take a look. We have Kix Jetpack Base. That's this bone here. And there are other bones attached to it. We have Kix L Jet 1. That's this bone. And Kix R Jet 1. So we actually have a bone for each of these jetpacks. So these are going to be the bones that I want to add sockets and attach them to. So I'm going to right click on Kix L Jet 1 int and select Add Socket. And right away, that's an awful name. So I'm going to rename this to thruster underscore L because we're on the left jetpack thruster. Now, we can change the transform of this socket relative to the bone it's attached to. It can have an offset, rotational and translational. But I don't know what that offset should be because I can't see the Niagara system that I want to attach to it. Well, Unreal Engine has a really nice feature to preview what it would look like if we attach some asset to a socket. We can do that by right-clicking on the socket and choosing Add Preview Asset. We can attach a preview asset such as a mesh or even a Niagara system. We want to attach a Niagara system, so I'm going to choose NS Jetpack Thruster, and there's that thruster. And as we can see, it doesn't quite look right. It's not oriented correctly, but we can change the socket's location and rotation relative to its parent bone. Now I have snapping on for rotation. I'm going to set its snapping increments to 10, and I'm going to rotate it by 90 degrees so it's facing down the thruster. And I'm also going to hit W to go to translation mode and move it on down like so. Now, I'm going to need to actually tweak this a bit. So I want to pause my animation for a second and move that thruster socket so that it's looking about right. I want it to be right here coming out of the jetpack, right? So something like that should do it. And now I can press play and I can see that it looks a lot better. Now that's just my left thruster. I need one on my right. So I'm going to pause the animations and add a socket to my right jet bone. I'm going to right click, add a socket. Right away, I'm going to rename it to thruster underscore R. Right click on that and add a preview asset and choose NS Jetpack Thruster. And just like the other one, it is not oriented correctly. It's 90 degrees off, so I'm going to rotate it by 90. And then I'm going to move it down. So we'll go ahead and bring it down like this and make sure that it looks good. We might have to tweak it a little bit, like so. And there we go. Make sure you adjust it until it looks just right. And now we have our thrusters. Make sure when you're adjusting these that you have the socket selected and not the bone. You do not want to move the bone. You want to move the socket relative to the bone. All right, and this is what it looks like with the jetpack. Now, this is only a preview asset. If we go back to Kix, we will not see those thrusters. All we did was add sockets to our skeleton. We can see them here in asset editors. I don't see it in that skeleton asset, but if I close it and open it back up, I do. So really, this is a preview asset we still need to actually add that Niagara system to our character, and we'll do that soon. For now, we have those sockets and they're positioned correctly. So if we do spawn in a Niagara system or add one to our character and attach it to this socket, it's going to be at the correct location, as the socket has the correct location relative to the bone. And that's what we care about for now. Awesome. And before we wrap up, I just want to bring your attention to the color of the flame. If we go back to our NS Jetpack Thruster, notice that our Niagara system has a sprite renderer. It's rendering this material, and notice it's a material instance. And if we browse to it, there are two different versions of this material. We have the material itself, and we have the material instance, which has a category thruster with some colors that you can override. Now you can change those colors, but I recommend not messing with these colors, but instead making your own material instance of the parent material by right-clicking, choosing Create Material Instance, and calling this MI Jetpack Thruster underscore yellow, for instance. And now I have this MI Jetpack Thruster yellow, and I can change my jetpack to use that MI Jetpack Thruster yellow. And this is the original material. If I save that, I can go back into the skeletal mesh editor and see what it looks like with this material. And if you really want to, you can take your jetpack thruster and change the materials by overriding them in that material instance. So you can make a purple flame or a red flame, and you can play with some of these parameters to make it look different. So I just thought I'd throw that out there. You have options to make that effect look different. You can even duplicate the Niagara system and have multiple versions of it as well. But I'm going to leave it at blue because I like the blue and I think it looks good on Kix. All right, so we now have sockets on our skeletal mesh. Excellent job, and I'll see you soon. Welcome back. Now our Kix skeletal mesh has sockets, and we know that if we attach a Niagara system to those sockets, it will be oriented correctly and positioned correctly. Let's test that theory though by adding a Niagara system to our Kix skeletal mesh. Let's add two of them actually, one for left and one for right. Now I'd like these to be components, and that way we can activate or deactivate those components at will, and we'll learn how to do that. So let's go to BP Kix, and we'll add this to our mesh. So we want these attached to our mesh because if we attach a component to our mesh, we can select a attach point. We can select a bone, or in our case, we want to select a socket because it has an offset from the bone that we need. So with our mesh selected, I'm going to click Add and search for Niagara and choose Niagara Particle System. And this one will be thruster effect underscore L. This one will be for the left thruster. Now notice it's attached to my mesh, but it's right here at the base of the mesh at the bottom. But we can specify a socket to attach to by selecting the thruster effect, scrolling up, and under sockets, we can choose a parent socket. It says none and it's grayed out, but we can click on that browse icon and choose a socket. We want thruster L, and that's going to place it right there where that socket is. Now, what I want to do is take my thruster effect and set its Niagara system asset by choosing Jetpack Thruster. And there we go. It's attached at that socket and it's at the correct location. It looks great. I want to do this for the other socket. So I'm going to select the mesh. I'm going to add another Niagara Particle System component, and I'm going to call this thruster effect underscore R. I'm going to choose its parent socket to be thruster R and choose its Niagara system to be Jetpack Thruster. And now we have two of them. And these are actual Niagara system components on Kix. Perfect. So now I can go and press play, and I have those thrusters, and it looks great. Now, if I'm moving around, notice we have this blur that doesn't look too good. And for this type of effect, that's not something we want. This is actually motion blur. And I can turn motion blur off for my project in project settings. I can go to Edit, Project Settings, and search for motion blur. And that's a checkbox I can deactivate. So now we won't have motion blur. So for this particular project, I want that off. And now if I move my camera quickly, I don't have that motion blur and it looks a lot better. Now, my thrusters shouldn't be on all the time. We should activate them and deactivate them, which means we're going to want an input action and logic to activate or deactivate our Niagara system. And all components have an activate and deactivate function, and we can also start them off not active by selecting the component, and under activation, we can uncheck auto activate. We can do that for both of them. So they exist, they're there, but they're not active. We can activate them at will, and just to test that, in BP Kicks begin play, we can place a delay for, let's say, 2 seconds. And after 2 seconds, we can activate these thrusters. I'm going to grab both of them and drag off and call activate. And we can plug both of these thruster effects into activate. And after 2 seconds from begin play, we'll activate both thrusters. Let's see what that looks like. We'll wait 2 seconds, and there they are. They're now active. So we can activate and deactivate Niagara systems at will. We're not going to do so with a delay, so I'm going to delete those. We're going to do so with input when we activate our thrusters, and we'll do that next. So excellent job, and I'll see you soon. Welcome back. We now have 2 Niagara particle system components attached to our mesh, specifically attached to sockets on our mesh, and these are our thruster effects. Now we can check auto activate in the details panel for each one to see what they look like activated automatically. But we want to activate these on demand with input. So for that reason, we're going to keep auto activate unchecked for each component here. And we're going to create an input action for activating our jetpack. So let's create that input action. For now, I'm going to go ahead and close all my tabs except for BP Kicks and BP Kicks Player Controller. All the rest of these can be closed. And we're going to go into our Blueprints input folder, into Input Actions, and create a new input action called IA Jetpack. I'm going to go ahead and leave IA Jetpack's value type to digital bool. Now we just need to associate it with keys in our input mapping context. So we'll open IMC Kicks Movement, add this mapping, and select IA Jetpack, and choose which keys we want to activate our jetpack. Now, for the keyboard, I'd like to use my left shift key. So I just clicked on the keyboard and pressed my left shift key. But for my console controller, I'd like to be able to activate the jetpack with my right trigger. So if I click plus to add a new control binding to this action mapping, let's see what happens if I click on that keyboard icon and I press that trigger button on my console controller. Well, notice that my control mapping is now set to gamepad right trigger axis. This treats that trigger as a pressure-sensitive input, much like a thumbstick, and it will have values on a scale from 0 to 1, depending on how far in that trigger is pressed, and that's not exactly what I want. So I need to go back and change it by going to Gamepad and searching for Gamepad right trigger and choosing the one that does not say axis. Axis gives us an axis of values from 0 to 1, whereas Gamepad right trigger is simply on or off, which is more appropriate for an input action that has a digital bool value type. So we're going to make sure that it's set to gamepad right trigger. And now we have an IA Jetpack input action. Now I'd like to activate and deactivate my thrusters based on when this IA Jetpack has been started and completed. Now we've seen that we can go straight into our character BP Kicks, right-click in the event graph, and search for IA Jetpack. And we can implement IA Jetpack here on the character, even though the input mapping context has been added to Kicks player controller. So if we wanted to, we can simply activate and deactivate our thruster effects here. And just to show how that works, we're going to do that. As soon as we've started our input action, our trigger has been pressed, or our left shift key, we're going to take our thruster effect R, and from that get node, we're going to call activate, and we're going to hook that up to started. Now we can also take our thruster effect L and hook that up to the same node. This is the equivalent of calling activate twice. Now, in addition to that, I'd like to deactivate our jetpack thrusters when our input action has been completed. So I'm going to drag off of thruster effect R and type deactivate and call that function and hook that up to completed. And I'm also going to take thruster effect L and hook that up to deactivate as well. So now we have only 4 nodes achieving this effect, and I can go ahead and collapse my input action node and give myself a reroute node here. I'm going to highlight the reroute and the deactivate node and hit Q, so they're aligned horizontally, and now our nodes look nice and neat. And we can test this out by pressing the shift key and the right trigger. So let's go ahead and press play. I'm going to hold down the shift key and I get my thrusters. I'm going to release the shift key and my thrusters are gone. Likewise, I'm going to get my gamepad controller and press my right trigger. I see that I get my jetpack thrusters, and if I release, my thrusters are deactivated. So everything works as expected. And this is great. We can actually say that we've accomplished our goal here. But if I'd like to handle all of my input in my controller class, just to keep that responsibility contained within the player controller, I can do that. I could implement IA Jetpack here and get my controlled character and cast it to BP Kicks. You see, the controlled character is a character object reference, not a BP Kicks object reference, and the character class does not have these thruster effects. It's the BP Kicks class that does. But I don't want to cast to BP Kicks from my Kicks player controller. And the reason is that creates a dependency on BP Kicks here in player controller. I don't want my player controller to depend on the BP Kicks class. I want it to be more generic than that. You see, managing your dependencies is something you do in good coding practice. I would be okay with BP Kicks accessing my Kicks player controller class, but I don't want that dependency to be going the other way from the player controller to Kicks, because I see my player controller as a more generic class that I should be able to use with multiple types of characters. So if I want to activate and deactivate my thrusters from the player controller, a good way to do so in a generic way is through an interface. I can create a Jetpack interface with Jetpack-related functions that my BP Kicks character can implement, and my Kicks player controller can simply call those functions on its controlled character. So before we wrap up, we're quickly going to create that interface. So I'm going to create a new folder in my Blueprints folder. This is going to be for my interfaces in this project. So I'm going to create a new folder called Interfaces. And we'll make our new interface here. So I'm going to right-click, go to Blueprint, and choose Blueprint Interface. I'm going to call it BPI Jetpack. So we now have a BPI Jetpack interface. And this function can contain Jetpack-related functions, such as Start Jetpack. We'll go ahead and make that our first function. And we can have a stop jetpack function as well. So stop jetpack. And these are generic functions that my player controller can call without having to know what class has implemented it. So first we'll implement start and stop jetpack in BPKicks. We can go to our class settings, into interfaces, and add our interface to the dropdown. We can search for BPI jetpack. And now we have those functions in our interfaces section in the My Blueprint panel. And we can simply implement these functions. I'm going to double click on them both. That way we have them implemented here as events. And we can simply hook them up to the functionality that we already have. Start jetpack, which in my case was on the bottom, now it's on the top. That's going to plug into activate, and stop jetpack is going to plug into deactivate. And now I can remove this input action IA jetpack altogether. And I now have the implementation here using my interface functions. And now my BPKicks character doesn't have to implement that input action. We can still keep the responsibility of that on the player controller. Now the player controller simply has to implement that IA jetpack. So let's go ahead and implement that. And we'll get our controlled character with a validated get. That's a good idea. Except we don't want this connected to triggered, we want it connected to started. And we want to take the controlled character and call start jetpack our interface function. So we're going to do that here for started. And we're also going to use a validated get for completed. And we're going to call stop jetpack when completed. And I'll go ahead and collapse that input action. So now we're calling interface functions on the controlled character without having to cast that character to a more specific class. I don't mind having our controlled character be a character, as we did perform a cast in our store essential variables function. We cast a character, but this is a engine class. It's more generic, whereas BPKicks is specific to this project. And if we plan on using our BPKicks player controller in any other project or with any other character, we would then have to perform two casts. We'd have to first cast to BPKicks. If that's valid, we access the kicks specific thruster effects and activate them. Then if that cast failed, then we would cast to whatever other character classes we're using, and that gets messy. An interface call keeps things generic and expandable as a code base. So now that we're handling input on the player controller, and we're handling the jetpack functionality on the character, and our player controller doesn't have to know about the character, it just has to call interface functions, and Kicks implements those functions. Let's go back and test this out one more time, and we see that our jetpacks are working. Perfect. So we see that our jetpacks are working, but we're not actually flying around. So far, our jetpacks just have a visual effect, so we still have some work to do. So we're going to continue our work on the jetpacks in the next video. I'll see you soon. Welcome back. Now we have our visuals working for our jetpack thrusters, but everything is completely silent. So in this video, we're going to handle playing the sounds for our jetpack. Now, if we go into our content drawer, into assets, we can find our sounds folder, and we have some sound effects under thrusters. We have three main sound effects. We have thruster loop, thruster start, and thruster stop. And these are meta sounds. And we can play each one to see what they sound like. There's our thruster start. That's our thruster stop and our loop. And that sound is going to loop indefinitely. So we're going to start playing some sounds when we activate our thrusters. Now, I don't think I need any of my input-related assets open, and I'm going to close BPI Jetpack for now. We're going to come back into BP Kicks, where we're activating and deactivating our thruster effects. Now we have this compact form where we only have 2 get nodes and our wires are crossing over to the different function calls. And this looks great for the case where we simply need to activate and deactivate our effects. But I'd like to separate things now because starting the jetpack now is going to involve more than just activating our thruster effects. So the first thing I'm going to do is separate these. I'm going to duplicate my get nodes for my Niagara components, and I'm going to break the wire on deactivate and just hook up my new get nodes to those. Now we have separation, and we're going to start up here with activate. So with event start jetpack, I need to play a sound for my thrusters, and I want to play this MS thruster start. So I'm going to spawn a sound at location. We'll go ahead and hook that up. And for the location, we're going to use get actor location. We'll just use Kix's location for this. And for the sound, we're going to choose that MS thruster start. Now, this is quite an intense sound. Let's just go and check how this sounds and how it feels in the game. So it lasts for quite a long time. If we start our jetpack and release the button immediately, we still hear that sound for a while, like this. So it's a little much, and I'd like to fade that sound out as soon as we've played it. Now, this is going to involve more nodes, so this is a good time to start collapsing things to functions. I'm going to collapse these 2 nodes to a function, and I'm going to call this start thruster sounds. So I'm going to open start thruster sounds, and let's just expand the dropdown for spawn sound at location. For one, this sound is a little bit loud, so if we want, we can play this a little bit quieter. I'm going to set the volume multiplier at 0.6, and as soon as I play this sound, I want to fade it out so that it doesn't last so long. And we can do that using the return value, which is an audio component object reference. That's what gets spawned by this node. And we can call fade out. I'm going to use fade out and set a fade out duration of 1 second. So the sound will only last for a second. And expanding the dropdown here, I see fade volume level. This means we're going to fade down to 0. And the fade curve is the trend that our volume will follow over the course of that second. It can be a linear fall off. For us, that's going to be fine. So now that we have a fade out, let's see how that sounds when we start our jetpack. So we have a 1 second fade out, and that sounds a lot better. But while our jetpacks are active, we're going to want to play a looping sound. Okay, so I'm going to collapse spawn sound at location, and we're going to spawn another sound, and that's going to be a looping sound. Except this one is going to be attached to Kix. So we need to use a different node. We want to use spawn sound attached. This is going to allow us to attach the audio component that gets spawned to Kix. So we have an attached to component, and that's a scene component object reference. We're going to attach the sound to the root component of Kix, which is the capsule component. We'll drag that in, hook that into the attached to component, and hook this up, and we can choose a sound. We're going to choose thruster loop, MS thruster loop. And we can expand the dropdown, and we have different options for this. We can specify the location. I know we're attaching to the capsule component, but this specifies where that sound will be depending on the location type. If the location type is keep relative offset, then this location is a relative transform from that root component. So we can leave that at 0. I'm going to set the volume multiplier to 0.6. We're not going to set attenuation settings. We'll leave everything else as is. So let's see how this sounds. We're going to go ahead and start our Jetpack. Now, we don't get rid of the sound. It stays even when we stop our Jetpack. But while the Jetpack's active, this sounds pretty good. But I'd like to fade this in so that it doesn't just start abruptly. Because if we bypass our spawn sound at location node and just spawn our sound attached like this, we'll see that that sound starts very abruptly. So I'd like a bit of a fade in, and we can do that with a fade in node. And we can choose a fade in duration of something like 0.35 seconds. Now we can see how that feels. And it's a nice gentle fade in. It's a little faster than our fade out for the spawn sound. So I can connect this back. And we now have the ability to hear our Jetpack starting, except when we spawn this sound and attach it to our root component, it sticks around, and we need to deactivate this sound. We need to stop it. And we need to do that when our thrusters stop. So in order to be able to stop this sound, to destroy it or deactivate it, we have to store it as a variable. So we're going to take the return value, promote it to a variable, not a local variable, because we need to access it outside of this function. And we're going to call this looping thruster sound. And I'm going to go ahead and give this looping thruster sound a category thrusters. Now, I'm going to set this value here, and then I'm going to use the value of my variable for the fade in. So I'm going to break that target and hook these two up. That way our nodes are clean. And I now have a reference to looping thruster sound that I can access when we stop our Jetpack. So in Event Graph, if we go to Stop Jetpack, I can take that looping thruster sound and check to see if it's valid by converting it to a validated get. And if it is valid, we can then call stop on this sound. And this should stop the sound. So now that we're stopping this sound, let's go ahead and see what happens if we release that button. And we stop the sound. Now, you might be wondering if we're getting a whole lot of thruster sounds being spawned in our start thruster sounds function, because we're spawning a sound and attaching it to our capsule component. You see, spawn sound attached returns a audio component, and we're storing that in our looping thruster sound. So the next time we call this function, are we spawning a new sound, and is the old sound still around? Well, we can always check looping thruster sound with a validated get or an isValid node. So I'd like us to understand what happens to looping thruster sound after we stop it. Let's bring in looping thruster sound and call isValid on it. We'll get the one with the question mark. And we'll do two things. If looping thruster sound is valid, we're going to print a string that says looping thruster sound is valid. And if it's not valid, we're going to have another print string, and we'll have looping thruster sound is not valid, and we'll go ahead and make that one red. Now we can hook these up and see the status of our looping thruster sound every time we start our thrusters. So we need to hook both of these up to spawn sound attached. And the first time I expect this looping thruster sound to not be valid because we haven't set it to anything yet. So the first time it'll be not valid, we'll get the red message, and then we'll spawn a sound and set looping thruster sound and call fade in. Now, when we release that key, we'll call stop on that sound, and when we press it again, we'll start this process over and see if it's valid. So let's go ahead and press play and start and stop our thrusters. The first time it's not valid, we'll release, and let's start our thrusters again. And look at that, it's not valid. Why is that? Well, if we go back and take a look at spawn sound attached and expand the dropdown, all the way at the bottom we have auto destroy. And it says whether the returned audio component will be automatically cleaned up when the sound finishes by completing or stopping, or whether it can be reactivated. So our spawn sound attached has auto destroy set to true, which means as soon as the sound is stopped, this sound will be destroyed and the variable will not be valid anymore. That's what's happening. But if we uncheck auto destroy and we go back and press play, let's see what happens then. We'll start it, it's not valid. We'll stop it, but we're not cleaning up that resource. So if I start it again, it is valid. But the problem is we're spawning in a new audio component and then storing that in the variable. So the old one that did not get destroyed still exists in memory. So what we've done is created what we call a memory leak. And if we start and stop our thrusters enough times, then we'll spawn so many sounds that we're simply stopping and not destroying that eventually our game could run out of memory and crash. And this is not something that you want in your games. So what we have to do is either check auto destroy and know that our sound is destroyed every time we stop it, or we can check to see if it already exists and only spawn the sound if it doesn't already exist. And if it does already exist, we can simply activate it by playing the sound. The way we have it now with auto destroy set to true, we're just spawning and destroying the object over and over again. Now, technically, this is more expensive. The action of spawning and destroying a component does require resources, whereas starting and stopping a component that already exists is cheaper. So I'd like to show how we can spawn a single sound and keep it around and just start and stop it rather than spawning a new one and destroying it every time. So here's how we do that. I'm going to remove these print string nodes. And we'll check our looping thruster sound and only spawn a new one if it's not valid, if it doesn't exist yet. That's going to be using spawn sound attached. So we'll spawn the sound if is not valid is true. And we'll store the looping thruster sound and we'll call fade in. But if it already is valid, all we need to do is play the sound. So we'll get our looping thruster sound and call play. So now we can start that sound and we can call fade in on that sound. So we'll duplicate fade in and use the looping thruster sound for fade in. So I'm going to duplicate that node and put it there. So in this case, spawn sound attached can have auto destroy set to false. And now we'll only spawn the sound if looping thruster sound is not valid, which it'll be valid after we've spawned it for the first time. And then we can go back in our event stop jetpack, and all we need to do is stop it when we no longer want to hear the sound. And now we'll only ever spawn one audio component. Let's go ahead and check this out. And it works. So that's a little bit of an optimization. We'll only spawn the sound once and keep it around, and we'll be calling play and stop on that sound as we start and stop our thrusters. Now the only other thing left to do is to play the stop sound when we stop our thrusters. So we're going to go ahead and take these nodes where we're stopping the looping sound. We're going to collapse those to a function, and we're going to call this stop thruster sounds. And here in stop thruster sounds, we're just going to play the stopping sound as well. So in order to play our stopping sound, we're going to use spawn sound at location. We're going to pass in the actor location, so using get actor location. And the sound I'd like to play is the stopping sound, which is ms thruster stop. And expanding this, we see auto destroy is set to true. I'd like to leave that at true, so we get our sound destroyed once it's finished. I'm going to set the volume multiplier to a lower value, about 0.4, and I'd like to fade this sound out by taking the return value and calling fade out. And I'll give it a fade out time of about 0.55 seconds so we can see how this sounds. We'll go ahead and start the thrusters and stop them. And that sounds pretty good. We don't have to worry about the memory of an auto destroy sound that we spawned. It will be destroyed when it stops. And because it's not looping, it will stop once it plays once. So we now have stop thruster sounds and start thruster sounds. And our event graph is looking pretty good. Our activate and deactivate could be refactored into a function, but we'll clean these up as we continue in the next video. For now, we have our sounds. It sounds great. Awesome job, and I'll see you in the next video. Welcome back. Now, we have some visual and sound effects working for our jetpacks. And it looks and sounds great, but it's not really functional. When we activate a jetpack, we expect to be able to fly. So this video is all about flying. Let's get started. If we go into BP Kicks and we select our character movement component in the details panel, if we scroll down, we'll see that there's a small section called flying. And we have a max fly speed and braking deceleration flying. The character movement component has movement modes, and by default, its movement mode is walking. But we can change its movement mode at runtime, and we're going to do that when we start and stop the jetpack. Now, before doing that, I'd like to collapse our activate and deactivate nodes. In fact, I'd like a function that can activate or deactivate it based on a Boolean input. So we're quickly going to create a new function. And we're going to call this activate thruster visuals. But we're going to have a Boolean input here called active. And we're going to get our thruster effects and activate or deactivate them based on this Boolean using a branch. So we'll set that branch right here. And back in our event graph, I'm going to just copy all of these nodes and come back to activate thruster visuals and paste them in. And for true, we'll hook up activate, and for false, we'll hook up deactivate. And now we have one function that can handle both scenarios. So back in our event graph, we can call activate thruster visuals here, passing in true, like so. And for stop jetpack, we'll delete that and call activate thruster visuals and pass in false. And we'll just quickly test to make sure we didn't break anything by activating and deactivating, and we see that it works. So now we have the sounds and the visuals. Let's take care of actually flying by setting our movement mode. And to do that, we need to get the movement component. And we can do that here when we start the jetpack, or we can do it on the player controller when we start the jetpack here, as we do have the movement component here on the player controller class. I'd like to handle that on the player controller class as it's related to movement. So I'm going to go to our essential variables section and drag in our movement component, convert it to a validated get, and from the movement component, I'm going to call set movement mode. Now, we don't see it here because our movement component is a pawn movement component object reference. But we can easily change this to a character movement component object reference if we go back to store essential variables and we instead cast to character movement component before storing our movement component variable. So after calling get movement component, I'm going to call cast to character movement component, and I'd like to change movement component to a character movement component. Now we can do this in one of two ways. I can change the type of this variable, or I can make a new variable of a new type and delete the old one. let's see what happens if we take this movement component variable and we change its type. We go to variable type and search for character movement component. If I choose object reference for character movement component, we get a warning that says this could break connections. Do you want to search all variable movement component instances, change its type, and recompile? That's what we want to do. So we're going to choose change variable type. And it's going to search for all instances, and this may create some errors that we have to fix. For instance, this set node here isn't going to work because now this is a character movement component object reference. So we can break that wire, and instead we can use the return from as character movement component. We're going to go ahead and hook that up and make sure that our cast is hooked up. And now we have a character movement component object reference. And if we click on compile and we don't get errors, then we don't have any other errors to fix. So now that movement component is a character movement component object reference, after our validated get here in our IA Jetpack, we can now call set movement mode, which is a function on character movement component. And we can change the movement mode on our character movement component to flying. Notice the dropdown shows us the movement modes. Walking is the default. We're going to choose flying. So we're going to set that to flying. And when we've completed our input action, when our jetpack is no longer active, we can now set this back to its default movement mode, which is walking. So we'll go ahead and set that back. And now we have a change in movement mode for our movement component, which belongs to BP Kicks. So let's just see what happens if we do that. But first, I'm going to run up to the top of this little hill, and I'm going to activate my jetpack here. And then I'm going to move off the hill. Notice that I'm actually floating. Now I'm going to continue floating until I get back to walking mode, and jumping works as expected and gravity works as expected. But as soon as we go to flying mode, we're now not actually affected by gravity, and we can move around in the world. And notice there's a very small degree of friction, so it takes a while to slow to a stop. And as soon as I deactivate my thrusters, gravity kicks back in and we fall. So there's just a couple of things I'd like to tweak about this mechanic. For one, I'd like to slow to a stop a little bit faster. In other words, if I start my thrusters and I start moving, I'd like to just slow to a stop right away and only keep moving if I'm continuously pressing the input keys. So to do that, I'm going to go to BP Kicks, select character movement, and on this component, I'm going to go down to the flying section, and I'm going to increase my braking deceleration for flying. I'm going to set that to a value of 200. And now we should slow to a stop much faster. Let's see what happens if we do that. I'm going to start my thrusters, and we'll see that we slow to a stop pretty much after a couple seconds. And that's the kind of friction that I want here in the air when I have my thrusters active. So that's the first thing I wanted to tweak with this. But the next thing is, as soon as I'm flying, I want to orient my rotation to the controller. In other words, I don't want to be able to move my camera around and see the front of Kicks. When I move my camera, I want Kicks to follow that rotation, at least in the yaw direction. And the reason for that is we're going to implement some flying animations that will look good when our character actually follows the controller. So there are a couple of settings to set for that. So back in BP Kicks Player Controller, after setting the movement mode to flying, I'm going to take the movement component and set a setting on it. We're going to set orient rotation to movement, and we want orient rotation to movement to now be false. I want to orient my rotation to the controller instead, which means we now have to set a setting on the character called Use Controller Rotation Yaw. Remember, if we search for controller in BP Kicks with BP Kicks self-selected, we have Use Controller Rotation Yaw, Pitch, and Roll. I'm now going to want that to be true when I'm not orienting to movement. So I'm going to get my controlled character here, and we're already making sure it's valid before we get to this point. And we're going to set Use Controller Rotation Yaw. We're going to set that to true. And we want the opposite of these settings when we stop our jetpack. So I'm going to duplicate these nodes, paste them down here. Only when we stop the jetpack, we're going to set Orient Rotation to Movement back to true, as we'll now be walking, and Use Controller Rotation Yaw back to false. So we're no longer using the control rotation. So let's see how that looks if we go ahead and activate the thrusters and we move around. We're rotating our camera, we're actually rotating our controller, and we're orienting our rotation to the controller instead of movement. But as soon as I disable my thrusters, now my orientation is no longer following the controller. It's now based on movement. Now notice with this setting, we just snap to this location. So a smooth way to do it is by simply taking our character movement component and setting the property on that allows us to smoothly interpolate to our controller rotation. Do you remember what that Boolean is called? It's called Use Controller Desired Rotation. If we set that to true, we'll now interpolate smoothly to our controller's rotation. Now I'm going to uncheck that when we deactivate our thrusters. And now if we rotate our camera around facing the back and we activate our thrusters, now we smoothly orient towards our controller rotation. This is using Use Controller Desired Rotation instead of setting Use Controller Rotation Yaw. So Use Controller Rotation Yaw is good for just automatically using the controller's rotation yaw, setting our character's rotation to follow that rotation yaw, whereas the movement component has the ability to smoothly interpolate to the rotation yaw. And that's better when we're transitioning into and out of this state. And of course, we can go to our character movement component and search for rotation, and we can speed that rotation rate up if we want to orient towards that direction faster. We don't have to use 720. We can use 1440, for instance, and we can go ahead and move our camera around and activate our thrusters, and we have a faster rotation rate. Just remember that that rotation rate also affects how quickly we rotate our camera, but 1440 is pretty quick, so we're pretty responsive. So now we're switching our movement mode, and we're also switching the way that our character is oriented. When our thrusters are not active, we orient rotation to movement. When they are active, we orient to the controller's yaw. And this will look a lot better once we implement some flying animations, which we'll do pretty soon. But I'd also like our thrusters to make us go upward as we're holding those thruster keys down. I'd like the thrusters to actually have some kind of upward force or perceived upward force. And we'll handle that next. But before we wrap up, let's just clean up our nodes here in the player controller, as we're doing a lot of things here, and we don't want our event graph to get out of hand, right? So we're going to collapse these to functions. And it's important to make sure the functions only do a specific thing. We don't want one function to handle too many responsibilities. Now, setting the movement mode is closely related to setting these properties on the movement component. So I'm going to collapse these nodes to a function, and these will be for setting the movement component variables when flying, we can simply collapse this and call it start movement mode flying. And we can collapse these other nodes to a function, and we'll call this start movement mode walking. And now this looks a lot better. And we could even collapse these to functions, but for now, we'll leave them as is. Our code looks nice and clean. It looks great on Kix as well. Excellent job, and I'll see you in the next video. Welcome back. In this video, I'd like to add some input to move the character up when those thrusters are active. Once we're in flying mode, I want us to be continuously adding input going straight up, and this is going to be a challenge for you. So while these thrusters are active, add input. I want you to add an input vector to the movement component. And since we're handling movement in the player controller, see if you can figure out how to do this from the player controller and only add this input while the thrusters are active. In other words, when the jetpack is on, and when it's off, I want you to no longer add that input. Then watch how I do it and compare your solution to mine. That's okay if your solution is different from mine. This is just a practice exercise. So pause the video and try this challenge now. Okay, so we want to add movement input, and I'd like to do this in the Kix player controller. And I'd like to add input every frame while the jetpack is active. Now, I could do this in Tick. I could perhaps set a Boolean to true or false based on when the jetpack is active, and then in Tick, check that Boolean and only add that input while active. That's a perfectly valid solution if that's what you did. What I'm going to do instead, though, is I'm going to use the triggered event on IA Jetpack, because I know that this triggered event execution pin is executed every frame while the input is active. So I really only need to call a function on triggered. So I'm going to add a new function, and I'm going to call this apply thrust input. And I'm going to take my controlled character and use a validated get for it. And I'm going to get my movement component and use a validated get for this one. So I know both of these are valid here. And on the movement component, I'm going to call add input vector. We know that this is how we're moving our character, but while thrusters are active, we're going to add an input vector up. Now, instead of hard coding just one in the Z here and moving in the world up direction, I'm going to get my controlled character and use get actor up vector. So I get my up vector of the character itself, and I'm going to multiply this vector by a float value. And this float value is going to determine just how much we're going to add that input vector. This can be a thrust factor of sorts. So I don't have to add a unit vector with a magnitude of 1. I can multiply this by, say, 0.25, but I'd like this to actually be a variable, and I'll call this thruster input factor. So its default value will be 0.25, but we can change that if we want to tweak it. And I'm going to add the input vector in this direction with this magnitude. And this will only be called onTriggered as long as I call it here, onTriggered. So I'm going to go ahead and call apply thrust input onTriggered. And really quickly, I'm going to set its category to Kix input. So it goes into the Kix input category. So now I can play test this. I can activate my thrusters, and we're going up. And if I deactivate them, I go back down. So now I can actually fly. And notice if I'm already going up, because I've jumped, as soon as I start flying mode, we still get a little bit of a drift. But because we have air braking deceleration, it's only going to last for a couple of seconds. So if I'm moving forward and I activate it, I'm going forward. So that's how that works. All right. So we now have a thrust input being applied on triggered, but when we're not triggering that input, we're not applying it. So we didn't have to create a Boolean and use the tick function. We're only applying this when we actually need it. And that's okay if you did use the tick function, that's totally fine. You can keep that solution or you can change it to the way I did it. Either way is fine. Technically speaking, not using the tick function in this case is a little bit better because we're not checking a Boolean every single frame when we don't need to. Checking a Boolean is a cheap operation though, so it's not really going to affect performance either way. And before we end the video, the last thing I'd like to do is refactor these nodes into a function, just because I like to see one node rather than three. So I'm going to collapse this one to a function called startJetpack. And I'm going to collapse these nodes into a function called stopJetpack. That's okay that they have the same name as the functions in the interface because Kix player controller is not implementing that interface. So these functions belong to the Kix player controller class. And we can give these the category of Kix input as well. And now the IA Jetpack looks nice and clean. I'm tempted to collapse these two nodes to a function, but I don't need to. Everything here looks pretty nice. And we're ready to move on. Great job, and I'll see you in the next video.